There. Okay.
Yeah,
So,
great.
okay, were you able to get that the course that I
Yeah,
mentioned
yeah,
at the
yeah.
top here? Oh,
Yeah.
good. Okay. Um, and were you able to get the code
Oh,
and
yeah,
get it
and
running?
I have already download PFC9.
Excellent. Okay,
Yeah.
so we should all be in good shape. We're not going to run the code today, but
Mm-hmm.
it's good that you got all those details worked out to be able to have it. Um, so what I'm just mentioning here is the whole idea here is to reach a point where you can be an effective user of the code, right? And I think of this like, the code you think of as like a tool, right? You want to build a table and there's various tools in your wood shop that you're going to use to do this. The thing that's a little different here is that you're not just going to build a table because you're not just going to do something that everybody's done before because you're doing a PhD. So you're going
Yeah.
to be using this tool and then you're potentially going to be doing new things in the form of probably developing new algorithms or something like how to add in fluid flow and things like that. So you need to actually not just know how to use the tool, but you need to have some reasonable understanding of how it works so that you can make some changes to it. Okay.
Okay, yeah, I think so.
And I'm sorry, go ahead.
Oh, I said that I think so. I should know
Yeah.
about that. How does it
Yeah.
work?
And so, yeah, so that's what we're gonna do all of that. And because I'm your mentor, this will all be fun and we'll, do it along the way here. Okay. So let's just jump into this here. Here's the big overview of the whole entire, what I want to cover in the entire course
Okay.
throughout the summer. We're only going to do the first one, PFC physics, right now. That is the key element here because how does this actually work? It's not just going to be a magic thing. It's going to be like, what's going on? What are the governing equations? And you already saw the governing equations. There's only two of them, F equals MA and F equals KX. Um, so we're going to talk about that today.
Okay.
Then the next time we get together, we're going to actually fire up PFC and we're going to begin building models. And in the process of building models, we'll talk about all sorts of different things. But the idea is just to do a very, very simple model that we can have as a thing in the background, like make a cloud of particles, turn on gravity, let them fall into a box and form a stable pile, right? Things like that.
Okay.
Then we're going to back up a little and talk about, because so by basically running the code, it would be like if you're just like my friend. I have all these interesting friends and they're not technical people, but there's still some of them, like I say, hey, come to my office, let me show you this thing I do. Like, what do you do for your work? They ask me. So I say, hey, I do this PFC code. And so it would be, this PFC in a nutshell would be like if one of those guys came into my office and said, what does this do? And I'd say, well, look, here we go. You just write like 5 lines and see the box and they're falling in the box. And, we're going to do stuff like that. Okay. That's the level of introduction there. Okay. Then we're going to take a step back and talk about the graphical user interface, but you're going to already see how that works basically because we're going to start working with it. Okay. So just like in the same way, if you got a new cell phone, I would just start showing you here, click on this, do that. And you might not even really, like nowadays, nobody even reads manuals for graphical user interface for cell phones, right? Because they're designed so
Yeah.
well. Well, we're still going to talk. You're going to need to know a little bit about the graphical user interface. And so we're going to talk a little about that. And then we're going to talk about this thing I call logics, which isn't actually a proper English word, logics, but I like the word. And this is going to talk about some of because PFC, it shares a lot of things with some of the other Itasca codes. And we're going to just talk about that. Like, for example, PFC is a command-driven program. So even though it has a graphical interface, you are actually you're writing, it's a script, effectively. Do this, do this, do this, right? Things like that. We're
Yeah.
going to talk about that stuff. Then we're going to introduce this embedded scripting language, which we call FISH. which are you familiar at all with Python?
Not at all, but well, I use a little bit of it before with the help
Hmm.
of AI to do
Oh,
some
geez.
simple work.
Okay.
Because I don't know about Python, but I have studied C++ or C
Yes.
language. Yeah. So
Okay.
yeah.
So that means you do have some knowledge of computer programming.
Oh yeah, but a little bit. I
Yeah, but
think.
that's good enough. So
Okay.
yeah, Fish is an embedded language in PFC, and it's very much like Python. And in
Okay.
fact, it was developed by Peter Kundal originally in the late 1990s in PFC before Python existed. And it actually is very much like Python. So it's the way that we're going to be doing more sophisticated things with PFC. So if you want to implement your own algorithm of something, you're going to be able to do that by writing code in Fish. Does that make
Okay.
sense?
Yeah,
Okay.
of course.
So you need to understand a little bit about Fish. And then we're going to talk about, bonded particle modeling, which is what you're going to be doing something related to that, right? You're not just going to be filling up particles in boxes and letting them fall into bins and flow around. You're not doing granular flow stuff. If you were, it would be quite trivially easy to use PFC. You just make a big bin with a bunch of walls and you make a bunch of particles and you turn on gravity and you let them roll. But you're going to be doing all kinds of you're going to be doing some more sophisticated stuff where we have to glue these things together, and there's all kinds of issues about, well, what do you mean glue them together, and how do we glue them together, and what are the properties of the glue, and all these different things. So we're going to then get to that, and then of course you're going to we're going to do your PhD problem, right? And we don't know what that is, so that's why I said
Yeah.
sky's the limit there, right? Okay.
Yeah.
Um, So the whole goal of this is the main goal of all of this is to get you and King, up to speed to be able to effectively use PFC now to address your still yet undefined PhD problem, right?
Yeah.
And in the
Okay.
process, I'm refining the course so that this can be used in the future as my next level course. All right? So you
Okay.
guys are like my guinea pigs, if we call it that. You know what guinea pig is? That's a
Yeah,
weird English term.
I know it's kind of pet, small, small animal,
Correct.
guinea
But it
pig.
also but in this sense it means like you're doing experimentation on the animal. Um
Yeah.
like a guinea pig, like a test, like a yeah, you understand.
Yeah,
You
I
guys
got it.
are, I'm going to be developing this as we go and seeing we're going to see how well it works for you to
Okay.
understand, right? Okay?
Mm-hmm.
So, that's the big plan. So here we go. There's me from a few years ago. That was before my beard was gray. Now you can probably see my beard is a little more. Oh, there you go. Now you can see me. My beard's a little more gray. What was that?
Maybe there's someone else in
Oh,
Shihang's office.
okay.
Yeah.
Sorry about that.
Oh, there we go. And so here, just because this is fun, see here's some of these different PFC courses over the years. You can see it's a good sign. Everybody's smiling in these PFC courses, right?
Yeah.
We have all these weird little toys. Like you're gonna see, we're gonna do something with this one. We're gonna do something with
Oh,
these two discs, right?
okay.
Then we had to have COVID and we had to do these online courses, right? So here's
Yeah.
various people. Who are these people? She's doing a PhD right now in India using PFC. She's looking at roadway ballast. So when you make a road, you have to dig a big giant trench and then you fill it with gravel. And then on top of that, you put the asphalt. And that gravel needs to get compacted and you want that stuff to be very stiff. And nowadays people put geogrid in there, which is a synthetic thing. It looks like a big net. and it makes it stiffer. And so she's doing laboratory experiments and PFC experiments to better understand that system.
Okay.
That makes sense?
Yeah.
This guy just finished his PhD, and he was used PFC to essentially come up with new ways to design GeoGrid, so it has different geometric configuration. And he used concepts of spider webs and how spiders
Spider webs.
create webs,
Oh.
because spiders are an example of a system that has the ability to make very, very structurally sound structures with very minimal amounts of material. And so based on lessons from that, and of course AI stuff, he came up with this certain algorithm to build different arrangements of this GeoGrid. And then he
Okay.
tested them in
Oh.
PFC. Isn't that cool?
Yeah. It's very new, like very new thing.
Yeah. And this guy up here is
Mhm.
works for a oil company in Thailand. It's the National Oil Company of Thailand, and he is the rock mechanics guy. And he has a big rock mechanics research laboratory with all kinds of testing equipment where they can take cores and they can do triaxial tests and heat them and put fluid in them and all that stuff. And he's also now beginning to do work with PFC to complement the laboratory testing that he does. So
Okay.
that's that guy, right? She's Marley, she just finished her PhD, and she was looking at taking sand and pumping a special fluid into it such that it cements the sand together. It's called biocementation. And the idea is you could be at a building site where the soil was not sufficiently strong, and you could make a borehole, pump in this magic chemical, let it permeate through the soil, give it a few days, and then it would cement it together to make it stronger. It's called
Oh.
isn't that cool? It's called biocementation.
Yeah, I'd never
Um,
heard of that.
um,
Biosemication.
like biological, because what they actually do is they put in bacteria, and these bacteria grow. And when they grow, one of their byproducts is something that's a lot like, it produces a cementation-like effect. So they call it biological cementation. There's a lot of research going on throughout the world to better understand that process. For example, how does the grain size distribution affect the resulting cemented material? That's one example.
Okay.
So she did a lot of laboratory experiments, but then she also did PFC modeling of that system to gain some better insight. Because in a lab experiment, there's a very limited amount of things that you can observe. There's a limited number of tests you can do, but there's also a limited amount of things. Like you can't actually see the really good detail of the damage that forms when you start breaking apart this biocemented thing. You can only see the fracture surfaces after it falls apart.
Yeah.
Right?
Yeah.
So you get the idea. So that's why we're doing things like PFC modeling, right? And the guy on the bottom right is in Korea, and he is working on a PhD. He just wrote a conference paper, and he's using PFC to better understand the damage behavior of hard rock deep
Uh-huh.
underground
Oh.
with excavation in it. And the question is there going to be damage on the surface of the excavation? And if so, what is the characteristics of the damage? How is it going to affect fluid flow? And he's actually using the subspring network breakable Voronoi model, this SNBV model, which
Oh.
is a recent model that I've worked to develop and is in PFC now, and is something that Frank thinks might potentially be an area for that you may pursue in the work you're going to be doing. Have you heard about this SNBV thing,
Yeah.
or? Yeah, okay.
I heard
It's
about
that
it.
paper. that I was all excited
Yeah,
about.
yeah, yeah. I know that
Okay,
paper
so
and yeah.
okay, so yeah, he's already been using that. Um, and then this guy is always smiling and happy. He smiles more than me, the guy on the left here. And he's in India and he's looking at again roadways, deep, not deep underground, roads, aggregate, this gravel that you put in the roadway, and how does it behave and things like that. So, and then there's other guys. We don't need to say everything about who they are or what they're doing. So here we go. Do you know
Okay.
what Star Trek is? This is an
Start.
American thing. Star Trek. Do you know
Maybe
what
I
that
don't
is?
know. Maybe I don't know.
A famous
Okay.
movie.
Oh,
Famous
okay.
famous
Star Trek.
movie, he says. Okay, well hang on. It's not wait, I gotta close the door because I talk so loud. All
It's
right, you're
like
gonna learn some American culture here, man. There's so much going on here. Star Trek. What is Star Trek? Star Trek originally was a television series in the late
televisions.
in the late 1960s. That's why it's in black and white.
Mm-hmm.
So I was a young child when this was a television series. And the idea was it's what we would call, I guess, science fiction. The idea is that this is humanity in, oh God, I don't know, like 6,000 years in the future. And they have the ability to have aircraft, spaceships that can like travel, throughout the galaxy. Um,
Oh.
and they they have this like well-defined, the ship is like this, goes on a mission, and it would be like, okay, we're going to go and investigate some new star system no one's ever seen before. And so when they do that, it's almost like a military thing, and they have a captain. So this is the captain here, Captain Kirk. Okay.
Okay.
And they have all these big exciting adventures along the way. Okay. And
Yeah.
then each show is about some of these adventures. Okay, so here's what's this one. So this is a particular episode that's called Spock's Brain. Now, who is Spock? Spock is this guy right here. Now, who's Spock? Spock is actually the second in command of the ship. Okay, so this is
Okay.
Captain Kirk, and this is
Mm-hmm.
the second in command. Now, he's also the chief science officer.
Mm-hmm.
And he happens to also not be human. He's Vulcan, which is like another group of people, but they're not human, but they're like human,
Okay.
right?
In the university?
Well, in the universe. I mean, there's
Yeah,
another
yeah, yeah.
planet, and
Oh, in the
they're,
universe. Yeah, not
yeah,
university.
yeah,
Sorry, I
yeah,
used the wrong word.
yes, got it. He's a
Universe. Yeah.
Vulcan, and he's very, very smart. Okay,
Mm-hmm.
he's very smart, and he's very logical. That's why he makes a really good science officer. Okay. Now, so in this episode, they're, in their ship, and they're going along, and they always show they call it the bridge. It's where the captain and the top people are there, and they can see in front of them, and that's where they're controlling the ship. It's the bridge.
Okay.
And they're on the bridge, and Spock, he's always monitoring things, and he says, oh, there's a vessel, unidentified vessel nearing us, da 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 da. So yeah, what is it? What can you tell me? All this stuff. And then all of a sudden, Spock just like disappears. Okay. Now the one thing you got to know in this world, there's a way of moving yourself from one place to another, where it's called teleportation, where you can basically do a scan of all the cells in a person, take that information on the other place, and then rebuild the person. So it's called transporting. So you can
Okay, I
basically
got
move
it.
things. Got it? One place to
Yeah.
another. Okay,
Yeah,
super
yeah.
cool idea.
Mm-hmm.
So it's not like magic, the fact that he disappeared. He's actually been transported onto this other ship. Okay.
Yeah, I got
And
it.
so, and then the ship just doesn't do anything. It doesn't make any further communication. And so, of course, Captain Kirk is going, bloody hell, we've got to get Spock back. Okay. So after many different things that go on, eventually Captain Kirk gets onto the ship and is able to gain control of the ship and find Spock. Okay, so what's happened to Spock? What the ship did, they basically stole Spock, right? Here you are, Spock, and they took his brain. They literally took
Okay.
his brain out of his body and they put it in the middle of their ship and they hooked up all the entire computer systems to his brain. So his brain was then running their whole entire ship.
Oh, okay.
Okay, isn't this kind of crazy? Um,
Yeah.
but in the process, they didn't kill his body. So basically, when Kirk comes, he's like, "Where's Spock? Where's Spock?" You know, and then they say, "Oh, he's controlling our ship." And he's like, "What the hell? What do you mean he's controlling your ship?" Right? And they take him into this room, and there's this box, big giant box in the middle, and you can see his brain is there with all these wires sticking out of it and stuff, right? And then his body is
Got
sitting
it.
next to it, right?
Oh,
Okay. And then, he's like and then of course, Spock actually can talk because he's running the ship. So Spock's brain, he starts saying, "Jim, my brain, I am running the entire ship," you know? And so then Kirk is like, "Flo, we've got to get you back. How could we do this?" Right? So there's also on this show the chief medical officer, and his name is McCoy. And McCoy, he's the doctor guy, right? And so he says, "McCoy, beam over here. We've got to get Spock's brain back into his body."
yeah.
And so, okay, and so McCoy says, "Jim, this is impossible. There's like 7 billion neural connections in here. There's no possible way that even our technology, we can never do such of a thing, right?"
Mm-hmm.
Um, and so, but of course, Captain Kirk he's never gives up. Okay, so he's like, "We'll figure out a way." He says, "Look, these people on this ship have the technology to do what they did. So therefore, there must be a database of this knowledge somewhere
Yeah.
in this ship." Okay.
Yeah.
So then they search and they find this library. Okay.
Mm-hmm.
Um, and in the library, there's all of these, it's all the information of this whole civilization, right? And it's all in the, who knows? They're not books, they're some kind of magnetic tapes and all kinds of stuff, right?
Mm-hmm.
And
Okay.
there is then in one corner of the library is this device, and it says on top, it says the teacher. Remember, here's where we're going, the teacher. There's
Uh-huh.
this device, it's the teacher. What is this thing? It's like a big helmet with wires coming out of it. And the idea is that you put that on your head and it
Oh.
conveys all the knowledge into your head.
Oh, wow.
Got it? That's why it's called the teacher.
Yeah.
Okay. Um, and so McCoy then basically has to go and put that on his head so that he can learn what he needs to do to be able to reconnect Spock's
They've,
brain to his body. Okay, got
yeah.
it?
Yeah.
Okay. Now, the reason I'm telling you all this is because this is kind of how I feel as the teacher of trying to get in your head all this knowledge that's in my head. I've been working on this stuff for many years and thinking about it for many years. And there's all this stuff I know about PFC and modeling with PFC.
Mm-hmm.
The goal here is to somehow get you to know that as well. And so that's why we have this question here. See, there it is. See,
Yeah.
so I'm Captain Kirk, and he's putting this device on McCoy so that he can learn all the everything, right? So
Yeah.
this is this is the idea of what I'm trying to do. And the thing I want to convey, to be effective at doing this, it's you need to interact as we go. You need to say, "Oh, I understand," or "No, wait, I don't get what you're saying."
Okay,
Um,
okay.
do you see what I mean?
Yeah,
Okay.
yeah. Completely
It doesn't
understand.
help if you just sit there and listen and don't give me feedback. It's not that helpful, right? You could just as
Yeah, yeah,
well,
yeah.
read the slides, right?
Yeah, yeah, yeah. So
So
I should say which I can or can't understand.
exactly. And I'm going to try to, ask questions along the way as
Mm-hmm.
well. And, that's why it would, of course, be so much better if we were in person,
Yes.
because
Yeah, yeah, yeah.
that sort of interaction is so much better if you're in person. But we'll do what we can. And hopefully I'll get to come out there in December, and then we can actually spend some time in person. Then I can, really ask you a lot more questions.
Yeah, of course.
Okay, here we go. So now
Hmm.
uh, a little bit about American culture, Star Trek.
Yeah.
Oh, and by
Oh,
the
and
way,
hmm.
go ahead.
Oh, okay. So, and it's like this. The Star Trek is a movie, and yeah, I don't know the English name about it, but for me, I love to watch the movies like this, like a
Mm.
star traveling or something. Yeah, I really
Oh,
like that.
good.
Yeah.
Okay.
Hmm.
Okay. Yeah. No, that's super cool. Um. Okay. So let's continue on here. Here we go. PFC physics. Now I'm going to go to another view graph here. Here we go. PFC physics. Do. All right. We'll begin with a thoughtful quote. What do you think this means?
Well, it's numerical modeling should be an aid to thought, not as substitute for thought. Okay, so well, I don't know every word, but I think um it's like new new sorry, I can check the meaning for the word that I don't know to understand it
Oh,
more. Yeah, I think okay. To aid the thought, but not a substitute for sort. Oh, um, oh, okay.
so thought is like thinking, knowing about stuff, right?
Yeah.
And so the idea here is that
Okay. Oh, yeah.
doing,
I
go,
I know
go
I
ahead,
know what does it mean. Yeah. I just
tell me.
checked the word substitute, and then I know.
Oh, okay.
Yeah. So
So
it's
tell me in your own words, what does it mean?
okay. Well, it's like we can't use numerical modeling to um we can't just put in all the situation and then take the data for uh uh f- not just take the data, but we should like think of a question and then think of how to build a numerical modeling and then we go the modeling, but not just do the modeling for the modeling.
Yes, that's the
Hmm.
idea. That's the
Yeah.
idea. The idea is that what you're doing is, in your case, you're doing some sort of research and you want to try to better understand something, right?
Yeah.
And so to help you better understand it, to provide an aid to your thinking about it, the aid to thought, modeling can be very helpful, right?
Yeah.
Um, but it's not, but you still have the key thing is it's just helping there. It's not replacing that, right?
Yeah. Yeah.
Um, and this is even more important for people who are not doing research, but who are, for example, maybe they're doing a design of a conveyor belt where it's or a big bin where there's granular material, I don't know, let's say corn, and it
Mm-hmm.
has to like flow through various chutes until it comes out the bottom. And they need
Mm-hmm.
to design that so that it has the right opening size and it doesn't get stuck and things like that, right?
Yeah. Yeah.
And so for those kind of people, oftentimes it's like, oh, well, the model is reality. All I have to do is put in all the boundary conditions and we're done. I don't have to even think about, does this even make sense, right?
Yeah.
I just accept what the model gives me, right? So
Mm-hmm.
that's what we're trying to get here. And this is a quote from a very, very good paper that you should read. And it's in the materials for the course. It's from 1988. It's called Towards a Methodology for Rock Mechanics Modeling. So this is about rock mechanics, and it's about
Okay.
doing modeling in the world of rock mechanics. And it talks about if you want to do such a thing, what are some things you should be thinking about? The word
Yeah, yeah.
methodology is a fancy word. It basically means, oh, how should you go about thinking about and doing modeling if you're going to do it in
Mm,
rock mechanics?
okay.
Okay. Um,
Wow.
it's a very classic paper in the field of rock mechanics and in modeling because it's very rare that people often don't think about modeling as its own sort of science, if you will. Um,
Hmm.
they tend to think that models are the real system, and they just want to get an answer. And
Oh,
if that's not the case, especially in rock mechanics, because there is so much uncertainty in the input
yeah, yeah, yeah.
that even if the physics of rock was 100% properly mimicked in the model, even if it was, there's
Hmm.
still not precise knowledge of all the property. I'm going to make a tunnel in this area and I have 6 borehole data, and that's all I have, right?
Yeah,
So
yeah.
right away, you have this issue. Well, what can you expect to get from such a model? You're not going to get a precise answer. If you ask the model and say, how much is the tunnel going to deflect? Is it going to do 2.5 inches? Well, depending on the material properties, it might be anywhere from 7 inches to 2 inches, whatever, right? Um,
Yeah.
and so it talks about those sorts of things. And it's important because often many people who know a little bit about numerical modeling often come from a structural engineering background, and there's
Hmm.
something called finite elements, which is now a very
Hmm.
common structural engineering thing. In fact, you said your parents do things related to that. Um, and so if you come from that background, if you build a structural model of, say, a concrete bridge, and you say, if I put a load of this much in the middle of the bridge, how much will it deflect? Well, you're going to get a pretty good prediction because when you build that bridge, you're using special material that's been very carefully controlled, like steel, for example, and what its properties
Hmm.
are. And
Yeah.
the structural physics of how a structure behaves under small strain, which is what a structure behaves under when you build it for like transportation, right? That's
Hmm.
a very simple, well understood um, physics. And so
Yeah.
that's if you put in the real material properties and the material really has those, you're going to get super precise answer, right?
Yeah.
And that's what people tend to initially think it's the same thing with rock mechanics, but
But
it's
it
not.
it's not. Yeah.
Okay, so the key use of models in rock mechanics, especially PFC models, is to gain often a better understanding of like the mechanism, for example. When this thing begins to fail, how does it begin to fail? Is it one crack? Is it a whole bunch of
Yeah.
cracks? Does a crack form, which then leads to something else happening, which then leads to something
Hmm.
else happening? Those sorts of things can be investigated with these models, for example. Like you can say, like this is what most of the people at Itasca are consultants to the mining industry. So these people get called. There's a big slope collapse at some mine in an open pit in Tanzania, and guys from Itasca get called. They fly out there and they go and look at everything, and then they have to come up with some scenario and say, well, it collapsed because X. And if we know what X is, then we can say, therefore, you should do Y, right? And we're going to
Yeah.
advise you to do Y. But unless you know what X is, you can't figure out what to do to prevent it, right? And the fact that it
Yeah.
failed means something in the existing way of doing things is was missed or was not understood well enough or something unforeseen
Yeah.
occurred, right?
Yeah. Yeah.
And
Yeah.
so, and so these people at Itasca who are mining consultants use the PFC code and other Itasca codes extensively to try and investigate hypotheses that they make. And they'll say, I think it might have failed because the groundwater got so high that it reduced the effective stress and that caused it to fail. So they can then
Yeah.
build a model, incorporate those
Mm-hmm.
things, see if they can get it to fail with properties that seem reasonable. And so
Yeah.
that's an example here, right? It's an aid to
Yeah, yeah,
thought.
yeah.
What they're okay,
Yeah, I
they're not
totally
able, yeah,
understand.
okay? They're not able
Yeah.
to build up the perfect model of everything and just get an
Mm-hmm.
answer, right? Because there's
Yeah, yeah,
there's
yeah, of
multiple
course.
physics of different things going on, right? So
Yeah.
so there we go. Read this paper when you get a chance. Let me just
Okay,
quickly
and
show you in the course material, which I'll send you. It's all just a
uh-huh.
simple thing. And right now, there's just a PFC physics right here, support materials. Can you see this?
Mm-hmm. Yeah.
And in here, it says papers, etc. And so, for example, Starfield and Kundal, I didn't put it in here. I'll go here. Hang on, just a second. Let me actually. I missed that one. It's because this is just a fun little quote, and I didn't. Hang on, you can see my weird little system of how I keep stuff here. Let's see. Starfield and Kundal. Boom. There, that's the paper. Look, see, it's such an old paper. It even is just a scan of something
Yeah.
from 1988. Okay. By the way, just as a secondary thing, the reason that I do what I do is because Tony Starfield was my professor when I was an undergraduate, and he got me interested in modeling.
Oh,
And that's the
wow.
connection of then, yeah, he's a fantastic professor. He's actually from South Africa, and he was an applied mathematician. So he's an applied mathematician. He's not a rock mechanics, or he's not civil, or he's not, he's mathematician, right? And
Mm-hmm.
in the world of applied mathematician, it's this idea of how can we apply math to actually address real world problems. So
Oh,
he's
oh, oh,
working at
I
this,
know that word. Yeah, 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 yeah.
oh, does
I
that,
know, I
okay,
know. Yeah, yeah.
applied mathematician.
Yeah, applied.
Um,
Okay.
and so he gave us this beautiful introduction to this world, basically talking about what's a model. A model is like a substitute for a real thing, right? And it's never perfect, but it can still be very
Yeah.
useful, right?
Yeah.
And then he has all these examples of models of things he's done in his life. Like he's worked with in South Africa, there are game preserves where they have wild animals that are nearing extinction, elephants, rhinoceroses,
Yeah, yeah,
things
yeah.
like that. Well, those game preserves have to be managed in terms of, what do we do? Do we let the animals grow out of control? Do we kill some of them? Do we bring in
Mm-hmm.
new ones? All those decisions have to be made. And so one of the things he did is he worked with these biology people who have to make those decisions, and
Oh.
he worked with them so that they could build a model of the game
Mm-hmm.
populations, right? Like,
Mm-hmm.
oh, what's important? Well, food is important. Okay, how important is food? Oh, something else is important. Hereditary, I don't know, whatever. And he
Okay.
talks about how we would work with these guys. These guys are not mathematicians, they're not modelers,
Mm-hmm.
but they somehow
Mm-hmm.
know a lot about
Mm-hmm.
managing game populations. But the
Mm-hmm.
problem is there's four guys in the room and they all have different ideas about what should
Mm-hmm.
be done. And so by making them work together and come up with a model that they think is reasonable, it allows them to better understand what they're doing.
Okay.
That makes sense?
Yeah.
Okay. So, that's an example of modeling, right? Tony Starfield ended
Okay.
up, he was in civil engineering at University of Minnesota when I was there. And so he
Oh.
did a reasonable amount of work in rock mechanics as well. And that's why he wrote this paper. And the other
Okay.
person was his friend and colleague, Peter Kundal. And Peter Kundal was a adjunct professor at Minnesota, and he's the person who developed the distinct element method. And PFC is a result of that. So Kundal was doing all this modeling at Minnesota, and at the time it was very new, this distinct element modeling. And then his friend is also a professor, Tony Starfield, who does all sorts of modeling. And so they got together. And my understanding is, Peter Kundal was always frustrated by people in rock mechanics who would take his models like PFC and just apply them in a not very intelligent way. Just expect that they're going to give perfect answers. And so they got sat down and said, hey, Tony Starfield, you think a lot about modeling. Let's write a paper about these things, right? So you should read the paper. It's a super interesting paper. We can talk about it
I would
next
do it.
time. Okay.
Okay.
All right. Now, since we're doing China, do you know about this legend?
Golden Sunbird. Legend of three-leg crow.
She's never been to Chengdu before, I guess.
I have been to Chengdu, but I don't know about that.
Shihong, help us here. What the real artifact that we saw? How big is it? How big is it? Like
about 10 minutes, 10 centimeters in diameter.
Okay.
Yeah.
Okay.
Just that big.
So it's like not a big thing.
Yeah.
It's not a big thing.
Yeah.
And the thing that I have here is even smaller. I'm sorry, I don't have a length scale on here. This is about 75 millimeters.
5 centimeter. This.
Okay. You can just hold that in your hand.
Yeah.
Okay. And this was so it has this symbolic significance, as I mentioned below here. Apparently, this was an artifact that was found in Chengdu at a certain place, which they call the Jinsha site. And now there's a museum there. And Shihong took me to that museum in the fall when I was in Chengdu.
Okay.
And as a souvenir, they call it, for something to remember this by, you can buy these little, this is a little, it's a little magnet. You can stick it on your refrigerator.
Okay, I got it.
And inside here, there's a thickness to this, and there's glass in the front and the back, and this is sand.
Okay.
This is sand.
Oh, so when you it will flow with
exactly.
when you
so
move
if
it.
If you rotate this, you're going to see this flow. Okay, and we're going to look at this in a minute.
Okay.
Because we can do this, and we can also model this. This is a super good example of, there's two things people do with PFC. They do granular flow, things like this. Usually those systems are not sticky. They're just dry sand. They just, they flow. If you have something that's the dry sand, for example, any two grains cannot sustain tension. You have two grains of sand that are dry. If you pull them apart, there's no force. But if you push them together, there's a compressive force.
Yeah.
So I refer to that as granular material, and the behavior of granular material is very sensitive to the shape of the grains and the size distribution of the grains. And then there is a very simple force displacement relationship that happens when two grains push together. And that very simple one we're going to learn about, and that's one of the what we call contact models that's in PFC.
Okay.
And you're going to learn that contact model, it only has 3 parameters, only 3 parameters.
Okay.
And every parameter is very, very understandable physically. And that model is used, and it produces the very much proper behavior of dry granular material, how it flows and moves. Okay.
Okay.
So this is going to be our example of a granular material. And then we're also going to show a quick example of what happens if we glue this together. So just think of this. This is sand. And if I rotate that, it's going to, you know, this is like an angle of repose here.
Yeah,
where it's
yeah.
stable.
But it will, yeah. It will
So
be
if
like
I
that.
rotate it, yeah, if I rotate it this way, counterclockwise, it's going to start to flow.
Yeah. But
because the angle's too big.
But when you see that, it should always be like this, right?
Yes, this would be like the final shape.
Yeah.
Right?
Yeah.
But then imagine that you put some kind of liquid, or let's just say, what if you took this and you heated this up, and let's just say that when you heat it up, when the places where two grains are touching actually melt together. And so now we have a cemented granular material. And so now that's going to behave very differently. That would be like a sandstone, for example, right? Like sandstone starts out as sand, and then it gets compressed, and then often there is fluid that goes through it, which ends up producing various chemical reactions that cement together the contact points. And then that is what sandstone is, right? So now we suddenly have a rock instead of a granular material. And the rock is made up of grains that now have cement. And so that's the whole world of bonded particle modeling, where we start with a granular system like this, but if we add the ability to have some kind of, I'll call it stickiness, I'll call it cement, I'll call it the ability to resist, to build up tension. We put that in there, we now have a bonded particle model, which is very much like a rock. Okay, does that make sense? That makes sense? Oops, did I lose you guys?
Maybe some internet problem, I guess.
Oh, yeah, hang on. We've lost Yun King.
Yeah.
How do I pronounce her name? Could you pronounce it, please, Shihang?
In Chinese, Guo
Yeah.
Yunqing, Yunqing.
Oh my God.
Okay.
Yunqing.
Yeah, almost.
Yunqing.
Yun.
Sort of.
Yun, the first character is Yun. Yun.
Okay, Yun. Yun.
Yeah, that's right. And
Yun.
the next one is Qing.
Qing. Qing. Ying Qing.
对
Ying
Yeah.
Qing.
Yun
Qing. Okay.
Qing. Yeah, almost.
Yun Qing. Okay,
Yeah.
I'm almost. Yeah, Yun Qing. Okay. Well, hold on. We need to get her back.
Okay.
Try to send her an email. Oh, she's back.
Yeah. Okay. Well,
are you back?
Wait a sec. Not yet.
Hold on. Let's see. Oh no, maybe she is. Hang on. I gotta admit. Oh wait, what happened? She's not here. Oh, did I lose you too?
No. Can you hear me?
I can hear you.
Okay.
Wait, I thought she got, okay.
Oh, she's back.
Oh, wait.
She's back.
Okay, is she in the, she admitted. Yongqing, are you there? So she's back on my system here. But I don't, she's not appeared here. Oh, come on. Ah, something happened.
Yeah.
There. Now, let's try this. Hello. Yongqing. That's not quite right. Ah, she's not here.
I'm talking with her in WeChat, so don't worry.
Oh, okay. I'll just wait then.
Yeah.
You can figure it out.
She's recollecting. Maybe something wrong with the software, and
Okay.
I advise her to use the web version.
Okay. Oh, of this crazy Teams thing? Is that the?
Yeah.
It's weird because it was working, right, to begin with.
Yeah. But always something went wrong with my software also. So I used the
Oh,
web
yeah.
version. Oh, it's
Oh,
really weird.
the web. Oh, I see. There's different types of Teams. Like you either have it installed on your machine or you can run it off the web.
Yeah.
Is it that thing? Okay.
Mm-hmm.
Do people use Teams very much in China?
No.
Okay, that's what I was afraid of. I imagine that there's a similar functionality of a different thing.
So in US, you use it frequently.
I don't know. People who are in the world of Microsoft do. And the
Okay.
world of Microsoft is a very powerful world that controls half the world. So yeah, it's the Microsoft thing for doing this. And
yeah.
Itasca has adopted all Microsoft technology about 2-3 years ago, so we use it now.
Okay. She's still recollecting. She's trying to recollect.
Okay. Oh, let's see. Now she got here.
Oh, I think maybe
come on.
She said she's all still loading.
Okay, that's fine. Don't worry, there's no big giant rush here. What time is it now? Is it 10 o'clock your time?
10 o'clock p.m.
Okay.
Yeah.
Okay. Okay. Trying again. One of these times it's gonna work. Have you read the Starfield Kundal paper, Xihan?
Oh, sorry, I haven't read that. This is the first time I know this paper.
Oh my God, you've got to read that paper. I will, yeah. I'll send you guys the current course notes and there, the PDF files in there.
Okay. I'll read that later. Maybe you need to permit.
I'm trying again. Okay, I've been doing that. Let's try again. Here we go. Well, see, this allows me to practice. So, yun, it's not yun. That's not, what is the first part? Yin, qing.
Yun, qing, yeah.
Qing.
Qing.
Yin, yun, qing.
It's the flat one, the first tone. Qing, qing.
Xing. Okay. Xing. I have my niece lives in Spain and she teaches languages, and we were talking a little bit about Chinese, about I started telling her about you teaching me the 4 tones, and she knew all about that stuff. She talked about certain languages are tonal, she called them, and she says that Chinese people tend to be able to learn other languages more easily than Americans.
Why?
Because your language is tonal, and so you're very, very sensitive to noticing slight differences in sound of pronunciation. Whereas an American like me, don't notice those things. It's just not part of my language, so the idea that there's different tones is not is hard for me.
Makes sense.
Yeah.
Makes so much sense.
It was really interesting. I was like, oh wow, yeah, that makes sense. How many languages do you know?
Oh, only two, English
Only
and
two. Okay.
yeah.
Okay.
I've never learned other language except English, but it's believed that the Chinese are easier to like learn like Japanese because the Japanese is maybe the language is not Japanese. Okay, anyway, it's derived from Chinese, so it's like simplest other language. Okay, she's still
Oh,
trying the
okay.
internet, and she
Yeah.
will give it a
Should
try
we?
with her iPad.
I don't know if it would help for us to start over again. I kind of think it won't matter. Because yeah, I think I think it's her end. Um,
Mm-hmm.
Can you would you like to continue coming to these sessions
Yeah, sure.
if you can?
I'd like
Okay.
to join this course. Actually, it's really
Okay.
interesting to hear
Okay,
about the
good.
Star Trek thing.
Can you then meet the same time a week from today?
Sure. I have
Okay.
time.
And for today, right now, could you stay for an extra hour or is it getting too late?
For me, it's okay, but I'm still in office, and the some staff would I can stay here for another 1 hour because this building is
Oh.
going to close.
Oh
But
my
for
God.
Yingqing is okay. And after we're
Oh,
back, yeah.
yeah. I see. Okay. So that's interesting. So you actually are limited. You cannot be in your office at midnight.
Yeah. This building is going to close.
So the
After
entire building closes, even for grad students.
yeah. After 11 o'clock p.m.
Yeah, okay. Um, yeah,
But
interesting. There was a guy many years ago who worked for Itasca and he used to come
she's
in and
back.
work all night long.
Oh,
Oh, I can see you.
hi. Finally, it works.
Excellent. Okay, we can hear
Yeah,
you.
I'm sorry for that. Maybe my computer, there's something wrong with that.
Oh, that's okay. That's
Yeah.
totally okay. I kind of lost the thread of where we were. We were talking about the Kundal and who knows what we were talking about.
I think we're talking about
Okay.
the
The
rock something.
granular. Yeah, we were talking about the granular material, and if you add bonding, it becomes a rock.
Okay.
Okay. A couple logistic things. So Shihong, we need to stop at 11 o'clock your time because otherwise he'll be trapped in his building, in his office.
Okay.
And can we meet again at this exact time 1 week next Monday?
Okay, I'm okay with that. It's well, it would be yeah, I'm okay with it.
Monday, June 30th. Okay. And
Yeah.
Shahong, and is it okay? Could we meet for 3 hours perhaps next time?
Sure. Next time I will be at dormitory, not office.
Okay. Is that okay
Yeah,
for
and
you
next time
too?
I will be at home, so it's totally
Okay.
fine for me.
Okay. Your parents are going to say, "What the hell are you doing? It's midnight. They're still doing research. Come on, go take a sleep." Okay. So, okay, then that's the plan because so that we know we'll just go as far as wherever we get to here, and then we'll for sure meet again next Monday for 3 hours.
Maybe
Okay.
today you can also do it 3 hours. I'll just make maybe a gap for 20 minutes, and when I'm back to dormitory and I join again.
Well, is that okay with you, Young King?
Oh, today? Yeah. It's okay
Today.
for me. Yeah.
Oh,
I
it
have
is.
enough
Okay.
time.
Okay, then if it's okay, let's do that. Okay. And Shihong will run back to his dormitory. Do you have the little bicycle? You have the bicycle, right?
Electronic bike. Okay.
Look at that electronic bike. Wow. Yes, they're everywhere in China. That was quite surprising when I was in China. Everybody has those electric bikes.
Very convenient.
Okay, let's continue on. So yeah, let's go for a little bit, then we'll take a quick break, and then we'll come back. But we're gonna go now for a total of 3 hours till midnight your time.
Okay.
Okay. So here we go. On the left, look at this. Look at all this stuff going on. We got 3 things going on. We got a discrete element PFC model in the upper left, and it's kind of self-explanatory what it's doing. You can see that's actually called the dynamic angle of repose, because depending on how fast you rotate a material, the angle of repose will be different. You can now see on the right, see this?
Yeah.
You can see it's like a landslide, right? And I
Yeah, I
think
can
that's
see
in
that.
some kind of clear oil, which makes it, you know, go relatively slow, right? Now this one, we're gonna.
Oh, sorry, I can't hear the voice.
Bonded
No,
material.
just see
It's
the
a
picture.
bonded material. Can you hear me? This one here?
Oh yeah, now I can hear all of
Okay.
you.
Hold on. Let me just a second. Let me go to the net just a second. Okay. There. Okay. This right here, red and white, is a collection of PFC discs that have been bonded together. Okay. And then they have been colored. So you can see the red and you can see the white. And then just for fun, they've been colored green. And do you know what this green is?
Jingle bell, jingle bell.
Oh, you got it. Okay.
Yeah.
You know that much about American culture. Okay, that's correct. Now, the properties here of this bonding are different. So for the red, it's just a granular material. There is no cementation, so there's no bonding. So that's like a granular material. That's like this stuff. It's like this stuff. But the white part has had bond put in. So that's like a sandstone. And then this material has been subjected to tectonic extension. So this is where in the far field, horizontally, it's getting stretched. And because it's deep underground, there is a compressive force that is being held constant as it's being stretched. That makes sense?
I get
Okay.
Get it.
And so if you watch what happens as we run this, you will see, you can see it stretching and you can see the bonds
Yeah.
breaking.
Yeah,
And you can see how this system somehow magically has transformed itself into a collection of broken pieces that have rotated like this. And this is what they see. This is an example of something in Greece whereby you see this system, what looks very similar to what's produced by the model.
Yeah.
And this was actually an example of, there's a fellow named Martin Schopfer, who is a structural geologist who has done extensive scientific use of PFC in the field of structural geology. And structural geology is the science of trying to explain and understand structural landforms. So he goes in the field and he sees this, and the structural geologist says, how did that get produced?
Hmm?
And so one of the hypotheses was that this started out as a single layer with no breakage, and that the top and the bottom were sheared. They were sheared.
It's like
Okay.
this.
Yes.
Yeah.
Like
So
this. Can you see me?
it will
It will
make
force it to break like this. That's
yeah.
that
I got
was the existing hypothesis. He said, I don't think that's right. because it's kind of weird. How the hell are you going to get shearing deep underground
Yeah,
like
but we
that?
don't get anything like this.
Yes. So he said he made a hypothesis that if you simply did tectonic extension with these boundary conditions, that this could produce the same result. And so this is
Yeah.
an example of the PFC model giving further evidence to back up his hypothesis.
Okay.
Okay.
Yeah.
And in the world of structural geology, they actually do this sort of thing, not with computers, but in the laboratory.
Oh.
So they create what they call sandbox models.
Mm-hmm.
So they would go in the laboratory and fill something up with sand and then cement a layer of sand and then do things to it and observe what happens.
Mm-hmm.
So they are able to use PFC as a way of doing a computer version of a physical sandbox model. Okay.
Okay.
And so that's why PFC is kind of accepted a little bit in his structural geology world, because it can be thought of as a sandbox experiment. And those are acceptable things that people do. Of course, with the model, you can also do, like you can apply loading here that you could never apply in a laboratory, right? You can do all kinds
Yeah.
of additional tests
Yeah.
with this, right? So in this case, he's not doing a sandbox model. He has the overburden stress at a certain depth that he's applying here, right?
Mm-hmm.
So this is an example, right? So there we go. So and there's your, there's your sand thing, and there's this. All right. So
Okay.
what do we mean by this bonded particle modeling, right?
Mm-hmm.
On the left, you actually have a real physical thing. Those are glass beads. Those things are, oh God, they're probably 25 centimeters, 25 millimeters across. So like you could hold that in your hand, but it's pretty small. Okay, so
Okay.
those are glass beads, and somehow they got packed together to begin with, in a cup, and then somehow epoxy was put in there, which is a viscous thing to begin with, and then it solidifies. And therefore it has cemented together the glass beads. And you can see how there's cement here. That's the epoxy.
Yeah.
And you can also see
Epoxy. Okay.
it's called epoxy. Yeah, it's a way of gluing things together.
Okay.
And again, it starts out as a viscous liquid.
Oh,
And then
epoxy.
it's
I heard this word. Yeah. I know
Yeah.
that.
Okay. And after
Yeah.
a certain, I don't know, 20 minutes or something, it solidifies.
Mm-hmm.
And you can also see after this has been loaded, how it's broken off, right?
Mm-hmm.
You can see here, right? There used to be a glass bead there. There used to be a glass bead here, right?
Yeah.
So we can, there's many different ways that we can bond things together. There's many different types of physics of what happens when you bond things together. One of them that we have in PFC is called a parallel bond. And the parallel bond is a very, very good mimicking of this system. Okay. And we're going to talk a lot about that when we get to bonded particle modeling. Okay.
Okay.
At this point, we can think of it as these yellow guys are disks that have been packed together. And now we have these parallel bonds, which are joining them together. So the black line there's a parallel bond between those two disks.
Okay.
And this system, in order to see this better, the disks are actually bigger than this. I'm drawing them smaller to make it clear that there's cement here. Okay. They're actually touching and there's cement there, but this makes it more clear. And when we do things with this type of model, whenever a bond breaks, this little color here that's tan, there's no more cement. So that gets removed. So when you look at the system, you're going to start to be able to see, oh, look, the cement is broken there. There's no longer that tan color. Okay. Okay. And we're going to see that. So if this was Peter Cundall's idea, or again in the early 90s. If we glue these things together, we're going to call this a bonded particle model. And PFC exists because in 1993, so about 1979, Peter Cundall was an adjunct professor at University of Minnesota, and he developed the distinct element method, and he had a research code in which he implemented it and wrote journal papers about it. And that code was called ball, like a ball that you bounce around. And that was a 2D code. And then a few years later, he wrote a 3-dimensional version. So now instead of having a ball, he called it a true ball. It's really a ball. It's a sphere. Okay.
Yeah.
And so he had done that, and there was many years where he would just give that away for free to researchers. So this was starting in about 1979.
Okay.
And but it would be free. Like, good luck. I'm not gonna. There's no manual. I'm not going to help you. Here's all the. It was a bunch of Fortran code, and there actually were many researchers in the early days who used that to do research using discrete elements. And then in the early 90s, Peter Cundall, throughout most of his career, was an adjunct professor at University of Minnesota, but he also was mainly an employee of Itasca. And because Itasca is in Minneapolis, it's, if I look out my window, I can see University of Minnesota 2 kilometers away.
Oh, wow.
Okay. So, Itasca then managed to put together a proposal to some companies and said, if you give us money, we will work with Peter Cundall and we will create a commercial version of his research code, and we're going to call it particle flow code.
Okay.
And so they got money to do that. And that's how the code PFC2D and PFC3D got created. That was about 1994.
Wow, that's very early.
And the people that did it was a big mining company that is interested in, they call it block caving. Caving. And so what is this? This is a way of mining material. So if you have hard rock deep underground and you have a large volume of rock that you want to get out, bring to the surface so you can grind it up and get whatever it is you want to get. Okay, one way to do this is you make a large amount of tunnels underneath, and then you basically keep making an excavation bigger and bigger and bigger, and eventually the roof of the excavation will collapse.
Yeah, I got it.
Okay, and now when material collapses, it bulks. They call it bulking. So what would happen is it breaks apart and it collapses, but then it fills up all the space, and now it's self-supporting.
Yeah.
So it doesn't collapse all the way up to the surface. It only collapses maybe 20 or 30 meters above where it started. It's a big pile of broken material. And then what they do is they just slowly take out the broken material, and as they do, it provides less support to the roof, and then it collapses a little more. And so when you do this, if it works, you can literally remove like 3 kilometers depth of material, and there's nothing left. Eventually, the broken stuff goes all the way to the surface. They call this block caving. You're making the material cave in. Okay, and so this is a very excellent way of mining, but it takes an enormous amount of money at the beginning to set up all of those tunnels, and you really don't know if it's going to work. And so it's a big gamble of an investment. And it also, I think it takes like 5-10 years of time to develop all those tunnels. And so you don't know if it's going to work till you've already spent all the money.
Oh, yeah.
because sometimes it doesn't collapse in a nice way. Like when it collapses, you would like it to break into, meter size or less blocks so that you can just pull them out with big machines. But sometimes that doesn't happen. And then then you're in trouble.
Yeah.
So this company donated some money to Itasca to say, you develop a code and we can maybe apply it to study caving. So that was one of the companies. Another company was a company that does something called powder compaction. So what's
Powder
powder
compaction?
powder compaction?
Okay.
So if you reach your hand out and pick up your cell phone, most likely you have a case of your cell phone. Can you see my case?
Yeah.
Okay. Well, this case is most likely created by powder compaction. So what they do is they take a powder and they squeeze it together into the shape they want.
Oh,
And then
okay.
I think they would also heat it. And what happens is the powder fuses together to form a solid material. And this way you can make very complicated shapes
Yeah.
because okay. And so one of the issues though is when you squeeze the powder, if you have corners in your shape, it might not push in there very well. And if it's not uniformly dense in the corner, it's not going to fuse together very well.
Yeah.
And so they also donated money saying, oh, we could use maybe this code to study how does a powder move under compression and how dense is it in different regions.
Okay.
So they gave money. Peter Kundal went and wrote this code. For the first 2 years, those companies were the only people who could use it. And after that, they said, you can do anything you want with it. We don't care. And so Itasca said, geez, I don't know. Why don't we try to sell it? Maybe we'll sell a few copies and make some money. And it'll allow us to do our own interesting research with it. And so that's how PFC got created.
Okay.
And as of now, so Itasca started selling this in 1996. And at this point, there's probably, give or take, about 2,000 licenses over that whole period of time that have been, sold for PFC. So that gives you some idea. There are, most computational codes like finite element codes, like Abacus or ANSYS, they probably have 1 million sales, right? PFC is like 2,000. Okay, so it's a very specialized thing, and it's mostly used by research people, either at universities like yourself or at big companies that are doing research on things, right? So it's almost always being used. It's used on things that people don't fully understand, and that's why they're using it to investigate hypotheses and things. Okay, makes sense?
Yeah. Makes sense.
Okay.
Yeah.
Okay, so this is the idea of bonded particle modeling. So that's what it is on the left. And now why do we care? Why does it matter, right? Because people are using it in the world of rock mechanics. Okay. And they're using it both for research to study new things, but some people are actually using it for applications of real things and getting real answers with it. Okay, I'll show you an example of that. The key thing that it lets you do is you can build a microstructure. And then once you build that microstructure, you can subject it to loading and you can observe the macroscopic response, right?
Yeah.
And the thing we're usually interested in is the damage.
Yeah.
And so the example here is a perfect example, right? You build a microstructure, you put some kind of properties of the glue, and then you observe what happens, right? And so with this model, you can control all these different aspects of the microstructure. For example, the shape of the grains, the amount of, strength of the glue, the size distribution of the grains. All of these things can be explored. Okay. And again, people are using it again for two things. For research, that's where I say scientific inquiry, trying to better understand things. So that previous model by Martin Schopfer, there's all sorts of journal papers he's written of that and similar things, gaining deeper insight into the behavior of rock. Okay. And there's also practical applications. Now, here's an example of a practical application. This is rock cutting. Do you know anything about rock cutting?
No.
Okay, excellent. That's why I'm going to tell you about it.
Okay.
We're going to come back to this. This is a PFC2D model that's been used by people in industry who make rock cutting bits. And it looks super cool. And we're going to look at an animation of this. But let's first get an understanding of rock cutting. So here's typically where rock cutting occurs in industries where you need to typically oil, right? You need to make a borehole deep underground. So how do you actually make the borehole? So what you have is you have a big string of steel pipes and you twist those. And at the very end of it, we call this a bit. So here's the end of the pipe. And you can see this has been cutting in some kind of probably sandstone-like material. So this is called the bit. So let's look closer at this, okay?
Okay.
Now look at this. This looks like a science fiction thing. Notice the length scale. So that's 400 millimeters, right? So it's not giant, but that's like a typical size of an oil well borehole.
Okay.
About 400 millimeters, okay?
Okay.
So how does this thing work? The overall thing is called a bit. And this thing screws onto a threaded pipe. And the pipe is connected to another pipe, and at the top,
very long.
it's being forced to spin. Okay?
Yeah. Okay.
And at the same time, it has a very high normal force because the weight of all those pipes is pushing down. Okay? So now how does it cut? It's made up of all these little, to me, they look like teeth. They call them cutters. Okay. And we're going to look, and so each cutter is being pushed against the rock surface, normal force, and it's being dragged in a shear motion across the surface.
Okay. So it's like,
okay. And so if we look at one of these, now look at my length scale. This is, this is like a watch battery. If you had a watch, they have those little batteries, or your calculator maybe has a little battery.
Yeah.
So you can see the length scale here, okay? This is actually some sort of a metal, and this is actually diamond dust that's been compressed and heated to form this very strong surface that has a very sharp angle. You'd cut your finger if you touch that angle there. Okay. They call this polycrystalline diamond compact. This is the part then that is pushed against, you can see right here, it's at some angle and it's pushed against the rock and it's forced to move. When it does that, if everything works well, it starts chipping in front of it, little pieces of rock chips form and break free. Now, the last thing that has to happen is if you just did this at the bottom of a hole and you started forming those chips, well, very quickly the whole thing would fill up with broken chips. And you'd be stuck. So what they do is this pipe is hollow. They pump fluid down here. See this opening? Fluid
so
then comes out.
These things.
Correct. So the pipe, the cutting, the hole is bigger than the diameter of the pipe. So fluid goes down the middle of the pipe, comes out the bottom, fills up with cuttings, and transports to the surface. Okay.
Yeah.
This is traditional technology of how rock cutting works.
Okay. Yeah.
And there are research groups, there are companies that build these things, right? Like they
Yeah.
build this whole entire assembly. Like this assembly probably costs about, I can't remember now, something like $12,000 US. Okay. And these things slowly wear out because they're not sharp anymore, right? And so
yeah.
think about this. You might be in the North Sea off an oil platform, and you have one of these things, right? This might be 2 kilometers in distance.
Yeah.
This thing
I
is
know
cutting. Let's say it's cutting for 3 days. Now
that.
it's not cutting good anymore. You
Okay.
spend an entire day pulling up all of this
Okay.
drill string just to replace this,
Change.
right? So the fact that this
Yeah.
bit costs $12,000 is trivial. Okay.
Mhm.
So the really important thing is that these bits last a long time.
Yeah.
And so that's why this industry is very competitive. If you can figure out better physics of how to build these things such that they last longer, then everyone's going to buy your drill bits.
Yeah.
Okay.
Of course.
So that's what motivates these companies, and many of them actually have research groups with rock mechanics people and others, because there's all kinds of mechanical engineering involved in building one of these things, right?
Yeah.
So the rock mechanics people, then they're interested in better understanding this. So there's been a reasonable amount of work modeling this with PFC. Okay. Now, the other thing to realize is that if you think of this cutter, and if you have you could do a test in a laboratory. You could just have a large block of rock, okay, like a sandstone, and you could make it into a cylinder, and you could take a cutter, just one of them, right? Just this. You could hold it down, and then you could spin the rock. And so this then is plowing out a groove as you go. Okay. This is a cutting test. And so what they do is they hold it at a certain distance down, and they spin it, and they measure force.
Okay.
Okay. And then they change things. Like they say, let's change the angle of this. And they see what effect it has. And then they do things like, let's change the detailed shape of this surface here, and let's see what effect it has. Okay.
Okay.
So those are called cutting tests. They're called dry cutting tests. They're relatively easy to do in a laboratory, and you can just watch them. You can take a video. You can see what happens. Okay.
Okay.
Now, you can do that, and it'll take a certain amount of energy to cut that rock. Okay. Now, if you take the same rock, but now you put it deep underground, and you're cutting now at the end of a drill string. Now, remember, I said there's all this fluid in here. This whole thing is filled with fluid because it's being pumped down and pushed up.
Yeah.
The weight of the fluid is causing a confinement on the surface of the rock. Okay.
Calling what? Sorry, calling what of the rock?
Oh, confinement. Confine. Do you know what confinement means? Push against the surface.
Okay, so it means that the water will affect the rock?
No, we're not talking about that. We're just talking about the fact that just think if this is a big giant thing, and I'm actually laying at the bottom of this big borehole, and there's no fluid. So there's no force pushing against me. I'm just on the surface.
Yeah.
Now you fill this with fluid. Now there's force pushing against me because of the weight, the pressure of the fluid.
Yeah. I got it. Okay.
And we're not going to worry about the fluid doing anything else except applying pressure.
Okay.
Now, and we call, in the world of rock mechanics, we call this confinement.
Okay.
You have like a free surface. So this would be, for example, in a rock mechanics laboratory, you would take a cylinder of rock, and you would put it between two steel platens and you would squeeze it. And the surface is free. They call that a unconfined compressive strength test.
Okay.
Then what they can do is they take the same specimen, but they put it in a rubber jacket, and then they put hydraulic oil pushing against it.
Okay.
So we call that confinement. So you could load it, but now you might have 4 MPa confinement when you load it.
Okay.
And it will take higher load before it starts to fail if you confine it.
Yeah.
Because for the rock to break, when it starts to break, it has to expand.
Yeah.
And if you prevent the expansion, it's stronger. Okay.
Okay.
So,
yeah, I know
so
that.
rock is the strength of rock is very sensitive to confinement. So when you're cutting, the same thing happens. So if you have this weight of the fluid applying confining pressure to the surface, it takes about 10 times more energy to remove the same volume of rock.
Okay.
Okay. And so there's two sorts of tests then that you want to do. You want to be able to do a dry cutting test, and you would ideally also like to do a cutting test that actually has fluid with confining pressure on there. Okay. And those second kind of tests are very difficult to do in a laboratory.
Yeah.
Okay. Nowadays they can actually do them, and they use mineral oil, which is a clear fluid, and you can actually see inside of it. So you can see the rock and the cutter, and you can see inside, and you could control all this. Okay. So this is a PFC2D model of the first case. I say free surface. There's no pressure. So what is this?
Yeah.
This is a 2D model. So these are little discs, and there's a lot of them. That's why you can't even really see the individual ones. Okay. And they've been compressed together to begin with, and then they've had bonding applied. So this is now like a sandstone. Okay. And this then is, think of it as like a brick that you've built. And then we're gonna basically put it in a little box, and we're gonna have, it's not gonna be able to move here or here or here. No, sorry, these two sides. The right side and the bottom side are fixed, so they can't move.
Okay.
Just the surface. And this is free, and this is free.
Okay.
And now we're going to have a cutter, and we're going to model the cutter, this thing. Now it's only 2D, so if you look at this from the side, it's just two surfaces that meet at 90 degrees.
Yeah.
And we're going to take that, we're going to put it at a certain depth, and then we're going to slowly push it from left to right, and we're going to watch what happens.
Okay.
And we're also going to monitor the force on that cutter.
Okay.
Okay. And the way we do that in PFC is the rock are discs glued together, and the cutter is something called a wall in PFC. And a wall is essentially a surface, and you can give it velocity. And it pushes against the particles, and you can monitor what's the total force pushing against the wall. Okay. So watch this.
Sorry for interruption. I have to leave for about 10 minutes or 20 minutes. Okay. You just keep doing
keep
this.
going.
Okay.
Sounds good.
Bye.
See you in a little bit.
Okay. See you later.
Okay. So are you ready? Here we go.
Yeah.
Watch this.
Oh.
Look at this. It's so cool.
Yeah,
There's actually two of them. This is more of a typical scenario. There's one comes front, there's one comes secondary.
Okay.
Let's stop this for a second. What is it that we're looking at here? So go back here. This is how we're drawing this thing, okay? So this here, if there's cement there, is going to have this color.
Mhm.
Now, if there's no cement, you're just going to see the yellow balls. So this
yeah.
system here,
Mhm.
notice right here.
Mhm.
This is just a bunch of broken part. They've all broken apart. These are just discs that are just pushing against each other. It's like a pile of broken rock.
Okay.
And the black, there's still all this cementing. There's all these cement bonds in there.
Yeah,
So this
yeah.
is like a fragment of unbroken rock. This is unbroken rock.
Okay.
This now, every time a bond breaks, we're going to draw a little red line.
Okay.
And we're going to say that red line is like showing us where it's broken. It's like a micro crack.
Okay.
Okay. And so
Okay.
what's happened here at this point is there's a whole bunch of broken bonds that have formed a big long fracture that looks like this.
Yeah. Yeah, I saw
Okay.
it.
Like watch this. You're going to see that same mechanism if we go back. Okay. Now it's going to start pushing and it's going to cause a crack to grow here and it's going to daylight.
Okay.
And that's a chip. There you go. Boom. This
Yeah.
happens really fast.
Yeah.
Now this is just a fragment of rock. So
Mhm.
now it's this fragment of rock eventually gets pushed, pushes against this unbroken surface, which will eventually make another fragment form. Boom. This happened really fast.
Yeah,
Watch that
really,
second
really
fragment.
fast.
Get ready. Here we go. Watch that happen again.
Okay.
Boom. And of course, now
Yeah.
that fragment formed. Now this is just a fragment, right? Now it's trying to push harder, but now it's just buckling,
Yeah.
right?
Yeah.
So this has already begun to form a fragment. I mean, this is not going to carry much load, but it's not going to, this is not going to move out of there until this guy gets closer.
Yeah.
Right?
Yeah. Yeah.
And so you're seeing this, these, you can think of them as fractures, these big red things, but there's really, they're like magic. They're just a whole bunch of bonds that have all broken and formed a single line, if you will. See, there you go. It
Yeah.
started to form a fracture, but it stopped.
Yeah. Yeah.
Part of the reason it stopped is because there's still some confinement on this thing. A fracture itself is very sensitive to confinement.
Okay.
If you have a surface forming in a solid, if you squeeze this way, it makes it harder for that fracture to grow.
Yeah, I
Okay?
can get this.
So it's sensitive to all these things, okay? And the other thing that you see in this simulation is that the surface of the cutter is almost never in direct contact with unbroken rock.
Yeah.
There is this broken layer of rock that's been ground up, and that's flowing as a granular material underneath the cutter, okay?
Yeah. I can see that.
Now, what's interesting, there's a fellow who was the head of a drilling mechanics group for a company called Hughes Christensen that makes cutters, and back in 1998, right after PFC came out, he contacted me and he said, I do research in rock cutting and I've heard about this bonded particle stuff you're doing. Could you model a rock cutter? And I'm like, I don't know. I got to learn more about the physics of rock cutting. And anyways, the big long and short of it is I set up this type of model for him. And he then went off and spent the whole summer running these models and making animations and looking at things. Okay. And he had a very important insight. And he said, oh my God, I think I've understood something that we never understood. And I said, what's that? He said, well, turns out that this shape here is very critical. Very small changes to this shape, they call this a chamfer. You can see how it used to be 90 degrees and then they cut off this facet. And depending upon how deep you make this and depending upon this angle, it has very big impact on the amount of energy required to cut.
Oh.
And
Wow,
as of that time, sorry, go ahead.
I think that's very I can't imagine that.
Oh, you mean it seems surprising?
Yeah, very surprising. Yeah.
Exactly. So in 1998, if you were a researcher in rock mechanics trying to understand this, you said the exact same thing. This is very surprising. I don't understand. Why?
Mm-hmm.
When you look at this model, the answer is right in front of you now as to why. So think about this. This rock cutter, most of the energy, most of the work that it's doing is basically forcing itself to flow over granular material. There's very little energy required to form these big chips. They happen really fast. And then most of the time you're grinding this across granular material. Okay. Now, what you have is you have granular material flowing along this surface. It's shearing along here, right?
Yeah.
Now, that is going to be highly sensitive to how it flows. And that's going to be highly sensitive to the surface geometry of what's going on here as it's flowing across there. Okay.
Okay.
This was an insight that he had, and this then helped explain why this system is affected by shape so much of the surface. Okay.
Yeah.
And previous modeling, which had all been done with what we call continuum methods, which are not discrete things like this. In a continuum model here, this is a continuum model on the left. This is a hunk of material. And you say, oh, this is going to be a continuum, meaning it's a theoretical thing whereby I could keep making it smaller and smaller and smaller forever, and it's always the same. That's what a continuum means.
Okay.
And so when we model things as a continuum, we don't have these fractures forming. All that we have is each of these elements, we call them, has what we call a constitutive model. It means this element, if it was subjected to this much strain, this is the amount of stress it could resist with. And, there's end up being a certain fundamental stress. It can't be strain. This is a strength, right? This is all parameterized. And so this is how we do things with a continuum system. We have a constitutive model, stress strain curves. Because this system, all it can do is it can say, oh, I'm not carrying load anymore. But the material is still there. So the cutter is still pushing against real material. And so it's completely lacking the ability to have this kind of localized mechanism occur where it's gone. It used to be a continuum. Now it's a granular system.
Okay.
So this is a key element of a bonded particle model. And so instead of representing things as a theoretical continuum, we're going to represent things as simply particles, which are just shapes. These are bodies, they're shapes. And these particles, and wherever they touch, we're going to call that a contact. And so here we have a bunch of disks, and they've been pushed together, and everywhere that they're touching, we put a little green line, which signifies a bond.
Okay.
Okay. And so you can see this is some microstructure now of bonded particles. Okay. Now we do not put a constitutive model in. What do we put in? We put in just for each one individually a simpler model where what we say is between two particles at a contact, this is the relative motion. Like we start pushing them together. And this is the force that builds up between them.
Okay. So
and
it's
then
like
maybe something happens.
Coulomb law, like that.
I'm sorry?
I don't know if I'm saying the right name. The Coulomb law. Coulomb law.
Spell it.
It's like Kulun.
Coulomb. No, I don't know what that is.
or maybe C oh okay, it's like COULOMP.
Got it.
Coulomb?
Yes, that's called a
Mm-hmm.
Coulomb law for
A
frictional
Coulomb
sliding.
law. Okay.
Yes, and that means you have a concept of a friction coefficient that limits the amount of shear force that can be carried. Yes, this is awesome that you know about this. That's what I actually drew here. That's one of the very simple PFC breakage models. So this would be shear force. This would be shear displacement. It loads, it reaches a critical limit and it slides. And then if you unload, it does this. So this is what you're putting in. You're not doing any continuum stuff. You're just doing a simple model at the particle contact level. That's it. Okay. So you're not working with stress strain. You're working with force displacement. Okay. In fact, in a bonded particle model, there never is a stress and there never is a strain. Such things do not exist in a bonded particle model. Stress and strain are mathematical averaging techniques that you apply to a continuum idealization. That's what stress and strain is. If you remember from here, let's actually try to do this. I'm going to try to share my screen and draw a picture on here. Share screen. Let's see if this works. Boom. Ooh, this is cool. I think it's going to work. Can you see my screen?
Oh, yeah.
Okay, now I just need to get this. Oh, come on. Oh, wait, my pencil turned off. Hang on. Okay, can you see my screen?
Yeah, of course.
Okay, so if you remember, I've assumed you've had a class about this. Have you talked about stress and strain? So remember when they talk about stress, they say, there's a continuum. It's some hunk of material. And then they say, let's take out a little region.
Yeah.
And then they say, oh, that region has tractions acting on it.
Yeah.
Right?
Yeah. Very familiar.
These are tractions. And then what they say is, oh, we can think of that as if this is X and Y, you can say, oh, so this is, let's call that F of X. You could say, we're going to define stress in the X to be this traction over this, right? It's going to be force in the X divided by, let's call this length in the Y. Length in the Y times thickness, right? And we're going to define this to be in the limit, and let's call this distance h. As h goes to 0 of this quantity is going to be what we're going to define as a whole new concept, and we're going to call it stress.
Yes.
Are you with me?
Yeah.
Okay. And so this is a mathematical way of saying, notice in this thing, we're taking the limit as this little thing goes to 0, which means you could take that continuum. It's a material thing. It's a real material, right? You could divide it forever, and it would never reach a fundamental length scale. There's no 0 scale. Now, for example, we know that that's not true. Our current understanding of physics is that that's not matter. You cannot divide it forever, right? Eventually, you're going to start to reach molecules, and then you're going to start to reach atoms and things of that sort, right? So there is in real material, there's a certain length scale below which the continuum assumption no longer applies. Make sense?
Yeah.
Okay. However, usually for engineering purposes, and usually even for rock mechanics purposes, we are operating at a length scale much bigger than the atomic scale. And therefore, this continuum assumption is extremely useful, right? And so everything, have you heard of this? They call it theory of elasticity. Have you heard of this?
Theory of elasticity. Okay.
Theory of elasticity.
I will search of it.
This is the kind of thing you may learn about in graduate school. And this basically
Theory
is
of
this
elasticity.
thing. It's basically relating stress to strain.
Yeah.
It's going to say, it's a theory that says if I have a continuum of any shape with any sort of boundary conditions, and if I apply any sort of load, how is it going to deform? What's the strain going to be everywhere? And what's the stress going to be everywhere?
Yeah, we have.
And so we call this theory of elasticity. So theory of elasticity was developed. So Newton first came along, and there was no concept of stress and strain when Newton came along. He just talked about bodies, and he talked about forces and accelerations of bodies. So he just talked about forces. And then people came along a little bit later, other mathematicians, and said, maybe a better way of thinking about bodies is as a continuum. And if it's a continuum, we can do things like we can define a thing called stress, and we can define a thing called strain. And then the relationship between stress and strain is what we call a constitutive model. Okay. And theory of elasticity developed these concepts. And now the vast majority of engineering and science that people do works in the world of continuum theory.
Yeah.
And so, like, when I started doing this work, it was like, well, someone would say to me, well, there is no such thing as stress. And I'm like, what do you mean there's no such thing as stress? It's a fundamental thing. And
yeah,
as you can see
I have
here,
the same question.
Yes,
now.
Stress is not a fundamental thing. Stress is something that is an emergent way of looking at a lower level thing.
Okay.
Okay, does that make sense?
Yeah.
It's like super
so
interesting
what is
stuff.
the fundamental thing, but not stress?
Well, well, here, I want to just a second. I want to stop sharing my screen.
Okay.
I want to get back to the slide. How do I stop sharing screen? Wait, how do I stop? Just a second. Okay, that's how I share the screen. Is this going to do it? Okay, did I stop sharing my screen?
Yeah.
And can you see my screen on this other thing? Can you see the slides?
Not yet.
Now you're going to see them.
Yeah, now I can see it.
Got it. So you asked, of course, the key question, what is the fundamental thing, right? Well, it depends on how far you want to go, okay, right?
Okay.
Now, the first level fundamental thing is what you see here, particles and contacts, right? Instead of idealizing a material as a continuum, we can we're still idealizing it. We can idealize it as a bunch of particles that are going to push against each other. And all of the strength is only going to happen at the cement. So what's a simplification? One that we could do. We could say that the particles, they have a shape, but they do not change shape.
Okay.
They do not change shape. They are what we call rigid. Rigid means they don't change shape.
Okay. Yeah.
And so then what we could say is, but when they push together, there's a little overlap that forms. And that's this overlap that forms. And there's going to be a force then that builds up, equal and opposite, pushes against them. Okay. So this is this idealization. So this would be like grains that are maybe like sandstone, that is quartz grains that are being pushed together. And the grains themselves are really not doing anything. All the action is happening at the interfaces between the grains. That's where all the deformation is happening. Okay. And so if we take this system and we build like an actual boundary value problem, and we then load it and we watch how it breaks, we could average that response and we could actually come up with a constitutive behavior. The constitutive behavior of this system would be an emergent property. And we would get different constitutive behavior if we put different properties of the micro properties here. So you could think of this idealization as more fundamental than this one. Because with this one, we can control, these are the properties we can start putting in, right? So for example, the size. There is, in this system, there's a length scale. You cannot really do anything smaller than this grain because we're not letting the grain break. So this system will never get broken into anything smaller. So we're never going to get, if these things are the size of a millimeter like sand, we're never going to reach the atomic scale with this. Okay. And of course, how they're packed and shapes, that's going to affect everything. And then of course, these different properties, stiffness, strength, how much cement, maybe only half of these guys have cement. That's going to be very different than if all of the guys have cement, right? So you can directly look at microstructure and you can see what occurs, okay? So the first level of answer to your question, what is the fundamental thing? You could say, well, this, you could argue this is more fundamental than this because this is the result of that. But then you could also say, okay, but let's start talking about every simplification I just made here, okay? You could say, well, okay, what about the grains? In reality, the grains do deform. They do change shape. Right? So if you added that, then you could say that's a bit more realistic, right? You could also say, well, the grains can break. So if you added that, you could say that's more realistic, right? All of these things can be done and have been done. We'll talk about this. But the other thing you could start to say, though, because now you're, since you asked this question, I love this question. You could say, okay, now let's take these grains and let's think that they're not rock. What if these grains were powder, little pieces of powder for the powder compaction? Now, holy crap, we got to change our length scale. The powder compaction, those things are like 5 microns in diameter. Remember, we talked about your hair. It's about 50 microns in diameter. So these powder particles are much smaller, okay? Well, now these powder particles, when you push them together, they don't just have simple force displacement response like we have here. They have things like electrostatic repulsion. That's why your hair, when it's dry, it like sticks, it like flies around because there's an electrostatic force. You start getting different physics going on when you get really small. Right?
Right.
And so one would argue that a more fundamental thing would be also having the different type of physics that occurs when you're small. Because if you had that in there, when you made the model bigger, it would also be like this, right? So that's more fundamental. But then, of course, it gets really crazy, right? Because then you start saying, okay, but then you come along and you reach a point where things are so small, you start talking about quantum mechanics. And so now you're getting to the boundaries of physics. Like, you know, can you take an atom, an electron, and a proton, and can you break that? What's inside of that, right? So, you know, this just sort of keeps on going. There is no 100% completely fully understood from completely basic low-level principles a description of matter. Okay, so that's the sort of the answer we have. We in your world of rock mechanics are going to be operating where you can think of these particles as representing actual grains of sand, for example. Okay. And at that level, it's a pretty good approximation to say that they're rigid and that, you know, da-da-da-da-da. We're going to talk about that. Okay. Okay. It makes sense? Okay. All right. Good. So this is the free surface case. So we built the model somehow, we glued them together, we put in bonding, and we observe this. okay?
Mm-hmm.
And we're measuring forces. Now, what if we then did a different case where now we have confinement of the, it's called drilling mud. It's not
Mm-hmm.
water. They mix in all kinds of crazy stuff to this fluid,
Mm-hmm.
so it looks like mud and it has more weight than just fluid,
Okay.
than just water. They call this
Okay.
drilling mud, and they do
Okay.
all kinds of special ways of engineering this mud to provide different things that they want.
Okay.
So that's why it's drilling mud. So what we've done is I implemented an algorithm that's able to apply confining pressure
Mm,
to this surface as it breaks.
yeah.
Now watch what happens now. Notice those chips, boom, they can't form because they're being confined on the top.
Yeah.
So the damage is completely different.
Yeah.
You're getting this broken up material, but it's confined too. There's confinement holding it together. And so you're
yeah.
getting this like broken up material that's flowing up the faces of the cutter. And you can see the rock out here hasn't even done anything yet.
Yeah.
It's much more localized.
Yeah.
These systems, just like in reality, this is what they see in reality. They
Okay.
see broken up material and it forms these big weird things like this. And then these
Okay.
eventually break off.
Mhm.
And it takes like 10 times more energy to cut. And so this is an example of an application trying to use PFC to look at the effect, because the question then, of course, is not only how does this shape and this orientation and everything affect the cutting energy, but how does the rock? What if I'm cutting a sandstone? What if I'm cutting a limestone? What if I'm cutting a granite?
Yeah.
So this allows them to begin to investigate, well, let's change the microstructure so it's a granite and it's not a sandstone, okay? Doing that is still at the level of research, okay?
Yeah.
This is not 100% understood. How can I make a microstructure of sandstone versus limestone versus granite? We're still at a kind of early stage in the development of this type of science, okay?
Yeah.
But so this is showing what's happening in 3D. So here now, this is a PFC wall, right? This is a bonded collection of spheres. We've made smaller ones here because we want to get a better representation of what's happening.
Okay.
And then you look at it from the side, these light guys are identified by the fact that there are no there's no cement anymore touching them.
Okay.
So you're seeing right here that for about 2 layers, these guys have fully broken free. So that's what used to look like the yellow guys in the previous thing, right?
I got that.
Right? And here's like depth of cut, 1.5 millimeters, 20-degree angle. Those are the kind of things people play around with in the models. This is another way of visualizing the system. These are the particles. They're being drawn transparently. And every time a bond breaks, we draw a little disc-shaped thing, which we're going to call a microcrack. And so these are the broken bonds that we have. So these things in 3D correspond to these red things here, these broken bonds. You see it better in this one, right? When a bond breaks, we draw a little red disc, a little red line. In 3D, we draw a little disc, right? The disc has the same diameter as the average diameter of the 2 particles that just broke at that contact, okay? And the other thing we'll do is we'll look at when it breaks, the way we have this simple model is it either breaks, there's a concept of breaking in tension, and there's also a concept of breaking in shear. And so we will color them to denote, did it break in tension or did it break in shear, right? And then one can speculate a lot about like what's the damage process, why is it in tension, why is it in shear, things like that. Okay, so this is the kind of stuff we're doing. And then here's the example of actually comparing the cutting force. This is the important thing. They're measuring force as they force the cutter to have a certain displacement. And in the lab, what they see is they get this big variability here. And this is because it's like this brittle behavior. Think of it. You think of, I like to think of, I live in Minnesota, so in the winter it's cold, and we get, sometimes we get ice, a thin layer of ice on the sidewalk. And if you want to scrape that off with a shovel, you could hold the shovel down and you push really hard, and then it breaks a little, and then you have to push again. That's what's happening here. It's the brittle nature of this.
Okay.
And so the discrete element model is doing the same thing, right? It breaks, it loads up, it breaks, it loads up. Okay. And so then from this kind of real data, they can take like a running average. And that's what this is, the mean cutting force. And then this, so they could take the whole entire run, and they can take an average, and they can do this for a certain depth of cut. Then they change the depth of cut. And so you can see that as you want to make the depth of cut bigger, it takes more force. Okay. And here's an example showing, they were able to construct a 3D discrete element model, and they're getting the same quantitative response, which is super cool. So that's what I'm talking about there. Okay. And so here's, so we good? Can you,
Yeah, I can understand that.
Okay, good. We've done the main thing here. Let's take a quick, I know we're only going to go for another 35 minutes, but let's take like a, I don't know, like a 10-minute break.
Okay.
Get her up, stretch her legs, and then come right back, and we'll finish things off. Okay?
Okay, no problem.
10-minute break. I'll just leave the screen running, okay?
Okay.
Okay, I'll be right back.
Okay. See you later.
听得懂吗？
大概吧，他就是，他就讲了那个，他刚刚在讲那个什么，就是钻头的那种什么作用，然后他就说，就是你刚刚不在那段时间，他是从什么地方开始那个，就是讲的来着？就你最后走的之前他在讲什么来着？
没关系，都是科普啊，现在都还是在科普阶段呢，没关系。
对，是我大概能听得懂吧，但是就是关于这个，他有说嘛，就是什么连续性和这个离散元的就是它的什么本质上的那个，叫什么，就是听太多了英文，中文也不会说了，就是它的本质有不同吧，他好像说的是，然后就是。
对，连续就是连续性假设嘛，就是这种东西，连续性的要更宏观一点，离散元要做的更微观一点。
OK，
所以离散元里
面，
你说，
就是说离散元它是基于那种，比如说每个颗粒间的那种接触，它是通过那种接触的分析那个接触的力来去分析这个。它比如他刚刚说的嘛，就是其实这里面并没有压力什么的，而是
对。
这个其实
它是这样，它这个地方指的应力呢，主要是指那个类似于弹性力学里面的那种应力和应变的那个概念，
就是应力应变的关系吧，它指的是。
对的，实际上你要说离散元里面有没有应力应变的，其实还是有嘛。就是看你怎么理解了，就 F 等于 ma 还有那个 F 等于 ks 这样的一个东西，其实也是力和应变之间的关系，
变形，对，
和变形之间的关系，对。但是它这边指的应力，你就以单纯的那个单轴压缩为例的话，你知道单轴压缩吗？就是岩石的或者沙的。
知道，就是没有微压这种的。
对，对，三轴就是有微压嘛，就是说，比如说你用 FLAC 去做那种单轴压缩或者三轴压缩的时候，它其实是基于一套那个 sigma 和 epsilon 它们之间有一套本格关系去算的。你给一个力，然后它慢慢算。但是离散元就不是这样做，离散元是把所有的颗粒啪堆在一起，然后压它，然后你计算的是颗粒之间的一个弹性的一个反应，而不是对整个块体有一个本构。大概就是这么理解，所以相当于离散元就是更微观一点，然后它们颗粒之间的一个弹性，如果你考虑弹性的话，当然它有更复杂的模型。 就是颗
OK
粒之间的这种弹性相互作用，最后表现为宏观的一个本构方程。所以其实
OK
现在有人做，不是用单纯的离散元去做了，他们就用离散元做一个本构出来，然后把这个本构套到那个物质点方法当中去模拟真实的应力应变行为，他们叫 MPM-DM。这样东西它就理论上来说比纯的这种连续性方法要更好，因为它不需要一个非常经验的本构，因为我是从离散元里面推出来的，但是它又能算大变形，相对离散元来说，它的好处就是它能做到更大尺度的一个计算。
哦，
对，
这样，
所以反正总而言之吧，今天讲到这儿，我看都还在讲科普，所以就
对，
对，可能最重要的就是当前这一页这样的一个东西了。你其他的一些你要基本有概念就行了。
好的好的，感觉目前还是暂时能听得懂，因为他讲的也比较简单，可能后面就不一定了。
对，然后至于刚才那个 confine 就是围压，就是有没有约束的那个意思。你也弄懂了，我也知道，我就是。
对，就是他刚刚说的是我也不懂，让他解释一下啊，我也懂了。确实
挺好的，现在都还挺基础的，就是还没有到有具体的东西的地方。
我看他一开始讲不是讲了他大概的那个计划嘛，他大概计划感觉也好像不会讲就是那么特别专门的，比如说某一个点什么，他就是讲一个大框架上的那种介绍，感觉。
对的，可能是吧，但是不要紧嘛，你其实具体的你在这个地方就是坡老师这个他带你呢，肯定是最好是大的带，小的需要有问题需要你自己去找出来那个问题才行。
那肯定是对，就是我感觉
对
可能也还好，就相当于是，就是也没有说讲的那么深入，因为是用英文嘛，如果讲那么深入的话，我肯定听不懂了。
其实你习惯就好了。我加这个课一方面其实主要是想听一下，因为蛮感慨的。哦，他回来了。
哦，他回来了，哈哈哈，哎，挺快的，没到10分钟呢。他可能不戴耳机，是不是听不见？他也戴了耳机才能听得见我们。
对，可能是的，没关系。Still on break 。
好的，是的，没错。
他要，
他可能还没有吧，他可能还要再 working 一下。哎，OK，我们可以等。哦，他戴上耳机了。
All right, I'm here. Can you hear me?
Okay, hello. Yes, we can hear you.
We can hear you.
Excellent. Okay. See, since I don't know any Chinese, you guys could be saying anything you want about me while I'm listening here, right? I'm sure it's all good. Okay. Hey,
Yeah.
Shihang, you're back. Hi.
Yeah.
Okay.
Just for me.
All right, here we go. This will be fun. Let's do a little bit longer. Here we go. How did we get here? Right?
Yeah.
If it was 1976, we'd be talking to this young long-haired guy, Peter Kundal, and he's like, I got this idea that if I take these things, I can model these things, right? So he goes and creates this. Here he is in the old days of the computer world, and he can do these amazing thing called computer graphics. This was like a really big deal. This computer graphics was a state-of-the-art, very expensive system that's sitting right here. So he created the research code, and again, he called it ball for 2D, and then a proper 3D was a true ball.
Okay, a true ball.
And that's the example that he has in one of his papers originally, and this was like a big deal. This was a big model to run. And you can see these are disks, and they've been pushed between walls, right?
Yeah.
And there's these little lines here you see. And so think of these as markers. When you first fill this, you just put them all horizontal. And then you start to squeeze, and you can notice the rotation. See, this guy has rotated. This is a way of looking at rotation. Okay. We can, of course, we'll play with this. We can do this with PFC as well.
Okay.
Here's a question. I keep learning stuff all the time. So I'm working with a student. She's looking at doing shear box tests on some kind of crazy material she's doing.
Okay.
And she's going to do PFC3D models. Okay. And so she's got different shaped particles to represent different kinds of material. And she wants to do a shear box test. And when you do a shear box test, you tend to get a localized region where there's large amounts of relative shearing. Okay. And she wants to look at rotation of particles. Because, you know, is it only the particles right in the middle of that layer that actually rotate? Or is it farther away? You know, right? She wants to see this.
Okay.
Now, if it was a 2D model, you could visualize rotation very easily by doing this.
Yeah.
And you could actually quantify rotation by just measuring the angle relative to the horizontal, correct?
Yep.
Okay, so it'd be very easy. Think of this. You built a 2D model and you actually monitor you sum up the amount of rotation in radians, because every time step, the particle has a velocity, a rotation velocity, and a translation velocity. So you could sum up for every particle all of the rotation increments. And when you sum them up, you would get the total rotation. Are you with me?
Okay, yeah.
Okay, so this is very easy.
Yeah.
But how do you do that in 3D? How do you, forget about PFC, how do you quantify rotation of a rigid body in 3D? Who knows the answer?
Well,
Shihong,
should we
come and impress me
add-
with your mathematical knowledge. Yeah, go ahead. Let's talk it through.
Should we add just like add 坐标 the word, and then maybe use a surface like a circle to simulate that, like the circle like this, and the face of it to turn it's the
Wait, hold on. I want to look at you. Oh, now I can see you. Go ahead. Talk again. Okay.
So
Use your
I'm
hands.
thinking
Okay.
about it's quite similar with what you mentioned before. Use maybe a circle and surface.
Okay.
Like this, and you can know the in
Orientation.
this side and maybe in this side. It's something like that.
So are you thinking of, take a sphere, let's just pretend the particles are spheres. Make it simpler.
Okay.
And I think what you're saying is, imagine you actually took a real sphere and you sliced it in half, and you stuck a disc that was bright red, and you stuck it on there, and then you glued it back together. Okay, you're saying that there's like a disc that's inside the sphere.
Yeah.
As it rotates, you can always look at that disc and see where it is.
Yeah.
So we could build this if we had a clear rubber sphere that we sliced in half, put in a red. Okay.
Yeah.
So that's what I thought. As of a week and a half ago, that's what I came up with as well. Okay. Then I asked a guy named Matt Provence, who in the world of PFC, it got created in 1994 by Peter Kundal. But he's not a professional programmer. Okay. He got it all to work and we could sell it and all that kind of stuff. But then it was getting pretty clunky and out of date. So in 2010, 2014, we spent 2010, it took 4 years. We completely rewrote PFC, starting all over from zero in a completely modern way. And one of the guys who did that was Matt Provence. And so in the process, there is a capability in PFC that allows you to track the orientation. And it's called orientation tracking.
Okay.
It takes a bunch of extra computation. So therefore you have to turn it on, because otherwise it slows things down. Okay. So I said to him, oh, orientation tracking, it's pretty simple, right? And I didn't talk about putting a disc in. I said, just take a sphere and take a black marker and draw a black line around the diameter.
Okay.
And just allow that black, just keep watching where that black line is.
Yeah. It's Same thing.
Okay, that's the same
Yeah.
thing, right?
Mm-hmm.
And I said, that's all we need to do, right? And in
Mhm.
PFC, you can do that. You turn
Mhm.
on orientation tracking and you define where that line is, you
Yeah.
know, and then it'll draw a line. You make it any color you want, and then as the simulation proceeds, you can see these lines, okay?
Yeah.
And he said, sorry, that's not enough. And I said,
Mhm.
why not? He said, think of the case where you have a sphere and you draw
Mhm.
your line like this, okay?
Oh.
Now it rotates around this direction.
Yeah. But it can appear.
You're losing
that.
information.
Yeah. Right.
Okay?
You're right.
So, just like, if we're thinking about an elasticity problem, we got to go back to the original guy. So the original guy was a mathematician named Euler.
Mhm.
Euler. I'm sure you've in
Euler.
different types of mathematics. Euler, he's very famous. He's done many
Euler angle.
Euler angle, yes. So Euler was able to show the following thing. In any three-dimensional, if you start with a zero state of a rigid body, and then it moves around for a while, and now you've got a new thing, and you want to get you want to figure out how much it's rotated. You can always describe it in terms of an axis and an amount of radial rotation about that axis. So there's two things needed. There's the orientation of the axis, but there also has to be the amount of rotation about it. And the axis itself keeps changing, right?
Yeah.
And so this is like the fundamental mathematics of what you need to do, right? So like in our case of that case where you had a circle around the diameter and you spin it this way, not only do you need to, we came up with the axis, but we didn't come up with this idea of also the angle. And so we call this thing, so the representation of this requires four numbers. It requires a unit vector for the axis, and it requires a scalar for the amount of angular rotation about the axis. And they actually, this mathematical system is called the angle axis. And so actually that's what PFC does. When you turn this on, you set the initial axis, and then it continually updates this. So at any time later, you can go to a particle and you can say, what's your current axis and what's your current angle? And then, of course, it's up to you to figure out how to visualize that, or what to do with it, right? So that's an example of the rotation. Okay, we're off. Okay, let's keep going here. So now can you see my screen again?
Yeah.
Okay. And so Peter did this in 79, wrote this paper, which is also in that set of papers. And this is like the most cited paper in all of rock mechanics. And so this is the paper. Everybody that talks about any kind of discrete element modeling always refers to this paper because it was the first one.
Okay.
That's, of course, in the world of scientific stuff. That's the reason it's been cited so many times, because it was the first. And everybody who ever writes a paper about this always says this paper, right?
Okay.
So you should read this paper. Peter is a very brilliant guy, and he's a very good writer, and he's very clear, and it's very simple. So you should read this paper, okay? And you should be able to understand. I want you to read this paper before next week. And I want you to read just those two. And I want you to read the other one, which I mentioned, the Kundal and the Starfield and Kundal paper. Okay. So bonded particle modeling. We began with a traditional distinct element model, which has no bonding. And we got this. Then we add this concept of bonding, and we get things like this, right? We've discussed this a little bit. That's a 2D model. Here is a 3D cylinder, and it's represented. The particles in this case are not spheres. They are actually polyhedra. You know what a polyhedra is?
What?
Take a plane, a polyhedra.
Polyhedra?
多面体。
Oh, okay, polyhedra. Okay.
Polyhedra means take a infinite body, make a cut of a plane, make another cut of a plane,
It's
keep
not a
doing that
ball,
until you
it's
have a single volume.
yeah. Okay.
So that single volume is made up of planar facets. And there's a special way of creating this thing called a Voronoi tessellation, such that we can fill an infinite body of space with a collection of polyhedra that perfectly fit together to begin with.
Okay. Yeah.
And this is what we then use as a starting point. And each of those, we call it a Voronoi cell, is treated as a PFC particle, which we call a rigid block. And then we have glue bonding and those on the facet on that interface. Okay. This actually is the SNBV model, that subspring network breakable Voronoi thing. This is potentially the thing you're going to work with. And what you see here is if you take that model and you give it properties like a hard rock, like a granite, then you can do triaxial tests. So remember we talked about a triaxial test. You squeeze it between steel platens. You either do it with no confinement. That's the black curve. You're measuring axial stress versus axial strain, and it loads up. It starts to fail a little, and then boom, it brittly fails.
Yeah.
That's exactly what rock does. That's what the model does. But then if you take the same rock and you put a sleeve of rubber and you apply fluid pressure to the outside, you can maintain that fluid pressure constant during the test, and you will get a higher value at which it begins to fail. So this is 2 MPa confinement. This is 4 MPa confinement.
Okay.
And also, if there's no confinement, it fails, it drops all the way to 0. Right? It just disintegrates. But if there's confinement, even after it has so-called failed, it still can sustain load. And so this starts to flatten out. And the more confinement, the higher that is.
Yeah.
This is exactly rock. This is exactly the model.
Okay.
So this is just an example of demonstrating that we can bond this stuff together in very intelligent ways in 3D, not just in 2D, and it behaves like rock. And so this is then a paper that I had the privilege, because I got to work with Peter early on in 1995 when I came to Itasca. He was just starting to explore these ideas. And we did quite a bit of work together, and we then wrote this paper called the bonded particle model for rock. And again, it's been cited many times because almost everybody that does this type of work says, oh, the original work was done, blah, 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 right? So, so that's what we're going to be talking about here, okay? So let's dive in here finally, okay? Here we go. So first, we're not going to get to bonded particle modeling really ever again until some number of lectures in the future, okay? We first have to understand granular behavior and how we model it with discrete elements, okay?
Yeah.
So what is a discrete element code? We're going to have one slide here that summarizes everything. So here we go. A discrete element code has to do, there's 5 things it has to do in order to be called a discrete element code. The first thing it has to be able to do is it has to have some idea of elements which are discrete. So it's called discrete elements.
Okay.
In PFC, we call these particles. These things typically do not change shape. They're typically rigid, but they don't have to be. Okay. The key thing is that you have these particles and they can move in 3-dimensional space and they can somehow interact in 3-dimensional space. Okay. So for example, do you guys have bowling in China? Where you take like bowling, you put these pins down and then you stand 10 meters away and you roll a sphere, a heavy one, knocks them down?
Yeah.
You do?
We call that another name.
But you know what I mean. So
yeah.
If you created a computer program where you could do bowling, that would be a discrete element program because you have discrete bodies, which are the pins, and they can move around and they can bounce against each other and all these things. Okay, that's what I mean by this movement and interaction.
Okay.
In the world of PFC, we have 3 types of particles,
Mm-hmm.
and they're called balls, clumps, and rigid blocks. So what
Okay.
are they? A ball is a sphere.
Ball. Mm-hmm.
In 3D, it's a sphere. In 2D, it's a disc.
Okay.
We can take a collection of spheres and disks and let them overlap if we want,
Mm-hmm.
and we can essentially create what we call a clump.
Mm-hmm.
The clump has the property that there's nothing happening here. It's just a shape, and it behaves as though it was a single rigid body that had that shape. So if something else pushes against it, it might get pushed here, it might get pushed here, it might get pushed here. But this thing behaves like a single rigid body.
Mm-hmm.
So it has a single centroid, it has 6 degrees of freedom, etc. So it's a single rigid body. Okay, so if we wanted to model bowling pin, we could have 5,000 overlapping little things that are one big rigid thing. Okay, that's called a clump. So it's a way of making a generalized shape, but the shape has bumpiness to it, right?
Mm-hmm.
Okay.
Yeah.
Then there, and in the world of PFC, these things that a collection of them creates a single thing called a clump. Those things are called pebbles. Pebble is an English word for like a little stone. So you have a collection of pebbles that can overlap each other, and that's treated as a thing called a clump. Okay?
Okay.
So the particles are balls and clumps, and we also can have a convex polyhedra. So that's where, this is a 2D version of a polyhedra, right? But it's a 3D thing. Okay?
Okay.
And we call that, in the world of PFC, we call it a rigid block.
Rigid block. Okay.
Rigid block, we call it an R block. So
Okay.
this is it. And in the world of PFC, there's going to be commands, and we're going to basically, there's going to be a command that says ball, create, or there's going to be one called R block, create, or R block, apply velocity boundary condition, ball, apply velocity. Every single command related to a clump is going to start with the word clump. Clump, da-da-da-da-da, ball, da-da-da-da. Okay?
Okay. I got
It's
that.
very, very logical, the world of PFC. And there's only 3. There's only 3 kinds. Okay? So in the world of PFC, these are the toys you have to play with, and they're going to move around like the real world.
Okay.
Now, they're also going to really be able to move around, meaning that, they might have started touching, but they can detach, and they can come towards each other, and suddenly, ooh, they're overlapping. There's going to be a thing called a contact. Okay? And so this has to happen automatically, right? So you just start the thing, you put all your bowling pins in there, and you roll a ball, which is also a particle, and it moves along until it comes in contact, and then a contact forms. And at a contact, there's going to be a force, equal and opposite, right?
Yep.
And so here's my example. These are 3 PFC particles, which are disks. They're yellow. These black things are walls, which are surfaces that can push against the disks. These surfaces do not push against each other. So what I have here is a box made up of 3 walls, and I have a separate wall on top, and what I've done is I've slowly pushed that top wall down. Okay? And notice nothing is happening here. Okay, the walls do not interact with, they're only surfaces that push against particles.
Okay.
So at this point, I'm squeezing these into this stable configuration, right? This guy has a contact. Every contact can have a force, equal and opposite. So the force then is pushing this way. This green line is a way of visualizing the force. So this is the orientation of looking at the force, drawing the force. We call this a force chain. And so, sorry?
Oh, I said okay.
Yeah, okay. So this guy, there's a force. It's pushing against the wall upwards. It's pushing the particle down. That has forced this particle to push against these 2, which has then made those 2 move outward. And so it's pushing against the 2 sides. This system here is in complete static equilibrium. Everything is balancing. If you take the total force acting on this particle, you have to sum up this one, and this one. They all sum to 0.
Okay.
Because if they don't sum to 0,
They will
because
move.
Newton tells us that the total force equals mass times acceleration.
Yeah.
So if the total force is not 0, that means the acceleration has to be not 0. That means it's going to
Yeah.
start to move.
Yeah.
Okay.
Okay.
So this is the idea. So this has to just happen magically. Contacts have to form. And again, if I like lift this up and start moving this up, these contacts are just going to disappear. They're not touching anymore. They disappear. They're not there.
Okay. Yeah. With
So
no
in the
gravity.
PFC, yes, if there's no gravity.
Yeah.
So in the PFC model,
Mm-hmm.
we're done. We're done with the whole course. All we have is particles, and there's only 3 kinds: balls, clumps, and rigid blocks.
Okay.
And there's walls.
Mm-hmm.
And those things, when they begin to touch, we get contacts.
Yeah.
Okay, that's
Okay.
it. And there's going to be all kinds of commands that are going to start with the word contact. You're going to
Okay.
say contact, do this, contact, do that. Put the strength of a contact in, da 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 da.
Okay.
Right?
Okay.
Okay.
No problem.
What else do we have?
Hmm?
Here we come to Mr. Isaac Newton, 1687. We're going to talk about that later. Came up with the basis of all of mechanics, F equals ma, right? So that's the equation we have to solve to allow things to move around properly.
Okay.
And so that's a differential equation, as we'll see, right? Because acceleration is the second derivative of position with time.
Yep.
Right? Derivative of position with time is velocity. Derivative of velocity with time is acceleration. And that's a vector equation. That's a 3-dimensional vector differential equation. And so we need to solve that. And so we're going to basically break up time into a bunch of small little chunks. And we're going to write, instead of writing it as a differential equation, we're going to write it as a couple separate little simpler things. Instead of change in velocity over change in time, we're going to say velocity at t plus 1 minus velocity at t divided by delta t. Change in velocity at discrete points. The new velocity minus the old velocity over the delta t. That's how we're going to write the differential equation. So the differential equation is going to become a couple very simple explicit equations to allow us to keep updating the positions and the velocities of these bodies. Okay? And we'll talk more about that.
Okay.
Okay.
I think I'm not completely understand about the sorry I
yes.
So maybe could you please explain it more? Or
yes.
Do you need any help?
No. Let me actually do this because this is so cool because I can do this. Let's see, share screen. Share screen without audio. Okay, hang on. We will talk about all this, but it's really good to talk about it here because you need to understand the idea, and it's not hard, but it's hard if you're just using words. So if I can show this, can you see my screen now?
Yeah.
Okay, now I got to get this one up. Okay. Think of this. Get out of there. Okay. Here's a particle, right?
Yep.
Here's force, F1 pushing against it.
Yeah.
Here's F2 pushing against it, right?
Yep.
So I'm going to say total force. It's a vector, so I put this squiggle under it. Force equals, and that's a vector. F1 plus F2, that's the total force.
Yep.
With me? This is the rigid body. So Newton says total force is got to equal the mass of that body. So this guy has a mass.
Yep.
Times the acceleration of that body, right?
Yeah.
Now, what's acceleration? Acceleration is change of velocity
and time.
Change of time. You with me?
Yeah.
Okay. Now, I'm going to approximate that to find a difference. I'm going to say, let's break time up into small little t. This is time.
Yeah.
T1, T2, T3. This distance is delta t.
Yeah.
So we're going to move forward in time.
Mm-hmm.
Okay.
Okay.
So I know the value here. I want to compute the value at delta t in the future.
Mm-hmm.
Okay. So what am
Okay.
I going to do? I'm going to take this is actually a differential equation. I'm going to approximate it as v at t plus delta t minus
Okay.
v at t divided by delta t.
Okay.
Does that make sense?
Yeah.
Now watch. Let's write the whole expression then.
Mm-hmm.
The resulting force equals mass times v at t plus delta t minus v at t over delta t.
Mm-hmm.
Okay.
Yeah.
Now watch this. I assume that I know everything at t, so I know this value. Okay.
Okay.
And let's assume I know delta t. I've decided what delta t is going to be, which means I know this value.
Yep.
Okay. It's a particle. It has mass. I know this value.
Yep.
This is the total sum of forces. So I know this value.
Yep.
Oh, look at this.
So
I'm
I
going to
can
find
know
the new
the
velocity.
next v.
Exactly. So v at the new velocity is going to equal force over mass. Bring that to that side.
Yeah. And
Times
then
delta t plus v at t.
yeah. Okay.
Right? This is the new velocity. So this is an explicit finite difference scheme.
Okay.
So notice it's explicit, meaning it means take small steps in time and move forward in time. That's what explicit means. And notice
So
that it allows me, it gives me a recipe for if I know the previous velocity and if I know the total force that guy's currently feeling, I can update the velocity.
Yeah. Okay. I totally understand now. Yeah.
I like it. Okay. Let me stop sharing this guy, and then we're just about done here. We'll just finish this slide. Stop presenting. There we go. Tell me if you can see. Oh, that's not right. Just got to get this slide back. Share. Boom. Okay, we back?
Yeah.
Just a minute. Go back here. 1, 2, 3. Okay. This is super awesome. It's really good that you asked me that question, okay? Instead of just kind of not following along, okay?
Okay.
So discrete element method, it has to do these things. So the fact that we're doing this is what makes it a distinct element method. Don't worry about this. The general term is discrete element method, and the particular way we're doing it makes it a distinct element method, okay? Because there's many different ways you could approximate that integral. You don't, not integral, the differential equation. One way is to do what we just said, and that's what we're doing in PFC, okay?
Okay.
The other thing is, this is a dynamic simulation. This means that we're always moving forward in time. And so at any given time, we know the position and the velocity of every single particle. And we also know how many contacts there are. And we also know what the force is at that contact. Okay. And so we're actually moving forward in time. Many simulations are static, meaning that you build a structure, you apply a load, and you get the solution for the final deformed shape. But that's not what PFC is doing. It's more powerful. It's a dynamic simulation. So it starts off as, here's the initial system, here's my load, and now we start moving forward in time, and we watch how the simulation progresses, how things interact, right?
Okay.
Okay.
Yeah.
Because it's a time stepping thing, that means there's a time step. Okay.
Yep.
And there has to be a way, if you have a really crude code, the user just has to select a time step, and you just have to use that all the time.
Okay.
It turns out, based on the mathematics of the finite difference equation that we wrote, you cannot make that time step infinitely big. and we'll
Yeah,
talk
yeah,
about
yeah.
this more. But the key element is that time step has to be small, and because if it's too big, that integration approach will not work, and the system will not follow the right path. It'll explode.
Okay.
So there's a critical time step, meaning that to make this work, the time step has to be the critical value or smaller. And if it's smaller and you run the simulation, you get the same answer. You keep making it smaller forever, you get the same answer. But if you get too big, suddenly it's wrong. It'll blow up.
I know that.
So, okay, and it turns out, we're going to talk about this next time, that critical time step is going to be based on the actual system itself. It's going to be based on the mass and the stiffness throughout this whole system. Okay, and PFC is going to, because it knows that, it's going to continually keep monitoring the current state of the system, and it's going to keep adjusting the time step. So when you run PFC, you don't really need to know about this. You just need to be aware that when you start taking, so when you run PFC, what you're doing is you're saying, take 600 steps. And that means it does 600 applications of delta T. But during that 600 steps, the delta T might slightly be changing all the time. Okay. So that's what's happening. And then the last thing, because it's a dynamic system, is there has to be some way of removing kinetic energy.
Oh, yeah.
Now, what does this mean? Think about if I have a box in front of me and I have some tennis balls, and if I drop them into the box, what do? They bounce around a little bit and then they stop moving.
Yeah.
And that's because in that real system, there is a damping type thing happening whereby that energy that I had originally ends up getting converted. Some of it gets dissipated through different means of damping. Okay.
Yeah.
And in the model, we're going to have different ways of making damping happen. Okay, so that when we're going to, and in the vast majority of the systems, we're going to use a special thing called local damping, and it's going to have a factor between 0 and 0.7. If it's 0 and we drop the balls in the box, they just bounce around forever. And if it's 0.7, they very quickly stop moving.
Okay.
And if it's in between, takes a little bit longer. Okay. That's what we're typically going to do in PFC. So this is the big picture. And now we're going to continue to unpack all of this stuff in the next lecture. Okay. So do you have any quick questions at the end? Did this make sense? That's my question to you. It seems like you've been following everything.
Yeah, I think so. Maybe. I think I can follow everything. Yeah.
Good.
And I ask everything that I don't know.
Good.
Hi.
This is working good. Yes.
Dave, I have one question. The
yes,
first,
please.
why PFC do not use or do not incorporate the superquadratic particles? We only have, like you said, the 3 shape. We don't use the superquadratic particles. Why?
So first, let me translate your question so that Yung King understands.
Maybe I can understand the superquadratic particles. Yeah, it's like we use the I know the things before from Shihang, so that
okay.
I think I can understand this question because I know that particles. Yeah.
Okay. Well, I'm going to say what I think I understand because I'm not an expert at superquadratics. My understanding is a superquadratic is a mathematical construction that allows you to have a small number of parameters that will generate a wide variety of particle shapes.
Yes.
That's correct. Okay.
Yes.
Yeah. All sorts of, in the ideal world, PFC would have every possible imaginable way of representing particles in it, but it's the real world and we don't have infinite resources. And so we don't have it. That's basically the answer. Again, you you could in principle do pretty much anything. If you could actually for effect, you could say, oh, I have a super quadric, set the parameters, boom, now I know the shape. I'm going to turn that into a polyhedra. Boom, put it in as a polyhedra in PFC.
Yeah.
Right? It wouldn't be exactly a super quadric because it would have these bumpy shapes, or put it in as a clump. It still wouldn't be exactly, but it would do that. So that's basically the reason. There's a bunch of, complication that occurs when you have a certain shape. Think about this. If you have a super quadric here, can you see me?
Yes.
Here's a super quadric, here's another one, and they have these crazy shapes, right? Well, you have to have an algorithm that's able to determine when those things start to touch. And then that algorithm needs to exactly determine the specific shape, all the details locally, and all the details here. And knowing those details, it then has to be able to figure out what to do with how you update the force and moment there. Okay?
Yeah. Go ahead.
So all I'm saying is adding something like a super quadric to PFC would require a large amount of stuff to be done.
Yes.
So that's the reason. Do you guys have super quadrics in a code you're using?
Yeah, I use the super quadric like in open source DM software. They have the contact algorithm, so I think in PFC we should have it because it seems convenient since the open source software have finished it. And the second question about the time step. I've been using the clump recently, and I want to know the time step when calculating the clump is determined based on the smallest pebbles or the overall clump, because I think it's maybe too small for me. If the pebbles is too small, I think it would maybe affect that.
I'd have to think about that. I don't know. Are you saying if you took a bunch of clumps, and you threw them in a box, you get a time step?
I think the time step for clump calculating is a little bit smaller than the sphere, than the single ball. And I guess this might because the pebbles in one clump is too small. I think the mass and the volume.
I see what you're saying. I don't think that shouldn't affect it because of what we're doing, but I'd have to think about that. It might be the case. I don't think it is, but it might. Yeah, there's all kinds of stuff about clumps that are going to make things go slower. So I don't know exactly. When we talk about the time step, we can think about that some more.
Okay. And I have last question about the rotation. Since I've talked about the superquadratic particles, and the rotation of superquadratic particles would be really important than the sphere, since the contact between spheres is always the same. We just use the distance and the radius to calculate the overlap, right? But when dealing with the superquadratic particles, different rotation status would have a significant impact. So we do not use the I cannot pronounce it right. The name of that sign.
The Euler angle.
Euler angle. We do not use the Euler angle. We use the quaternions.
Yes.
Maybe you know that. You will use the quaternions to do the rotation thing. Why do not we use this in PFC?
Well, there's a whole bunch of stuff going on there. The quaternion is just a detail of how you compute the Euler angle stuff. Fundamentally, PFC doesn't need to care about that. What it needs to know is how to do contact detection when two bodies come near each other. If they're spheres and clumps, it's relatively trivial. based on what you said. You look at the difference in radiuses and stuff. If it's a rigid block, it's a much more sophisticated scheme, which is going to be much more like what you're talking about. And you need to read about that in the PFC manual. It talks all about that. When it's a rigid block, basically when it's a rigid block, it's going to have a single overlap volume.
Yeah.
And it's going to always deal with the centroid of that. And it's going to look at the relative motion between the surfaces relative to that little overlap volume. So, I mean, that's all sort of that I could tell you. I mean, related to that. The quaternion has nothing to do with it. I mean, that's just a way of implementing some of this physics for these 3D bodies overlapping each other. And PFC does actually use that under the hood, but nobody knows or cares. That's just the detail of how it's done. But that is all described. That was all done by Matt Provence, and that is all described in the manual about how that stuff is done.
Yeah, I understood.
Okay.
Since I've used I code with myself, and I need to use the continuous from the software, and we need to use a rotation matrix to transfer it into the that angle, and we use and we
that's why you know about that
to,
stuff. Yeah.
Okay, thank you.
Okay.